This course covers the fundamentals of the Unix operating system. Unix is an essential skill for anyone working in technology today. Unix runs the computers and devices all around us, from mobile phones to supercomputers. It does not matter if you're using Mac OS, Linux, Windows, or a remote server. This course will teach you to use the command line to work with files and directories, to run Unix commands, and to configure your Unix workspace. We'll start with the basics and core concepts. We'll walk through demonstrations of the most important Unix commands together. You can follow right along with me or sit back and watch. Along the way, I'll share my advice and give you some real-world examples. You will immediately be able to apply your new skills to your own work. My name is Kevin Skoglund. I've been using Unix for over 30 years. I still use Unix daily for web development and anytime I need one of its many unique features. I'm excited to show you how easy it is to use Unix. Let's begin by getting an understanding of what Unix is and how it got to the point where it is today. Unix is an operating system. It was created around 1970 by AT&T employees working at Bell Labs. Many of the Bell Labs employees were involved in the design of a mainframe operating system called Multics, short for Multiplexed Information and Computing Service. Back then, mainframes were expensive, so users were granted time-sharing slots to do their work, often by logging in from a remote terminal with less computing power. Multics was designed to manage that remote login time-sharing process. But Multics became a large and complex project, and Bell Labs decided to pull out of it. But the employees who'd worked on it still liked the project's goals. So almost as a side project, they worked on building a smaller and simpler version. Their first version only supported a single user, so as a play on the name Multics, they called it Unix. Uniplexed Information and Computing Service. Uniplexed instead of multiplexed. Very soon it was able to support multiple users, and at that point they renamed it to Unix with an X. It doesn't actually stand for anything anymore, it's just Unix. At this point, Unix is a mainframe operating system being used internally by Bell Labs. But then two events give Unix a big boost in popularity. The first is that in 1972, Unix was rewritten in the C programming language. Prior operating systems were typically written in assembly, a very low-level programming language that required code to be written for specific computer hardware. It's very fast, but it's not portable. If you wanted to take your operating system to new computer hardware, you had to rewrite major portions of the code. The C programming language was originally designed to write programs for the Unix operating system. It's a low-level programming language, but not as low-level as assembly, and so the programs are easier to write and they're hardware independent. The developers liked C and decided to rewrite the whole Unix operating system using it. So Unix became portable to new hardware. The next important event is the spread of Unix outside of AT&T's Bell Labs. A court order in an antitrust case forbid AT&T from entering the computer software business. So AT&T could not sell the Unix operating system, but they could give it away. And so that's what they did. If you wrote to AT&T and asked for a copy of Unix, they would give you a free license and send you all the source code. Free high-quality software was very attractive to government agencies, corporations, and especially universities who'd bought these expensive mainframe computers. Unix spread quickly. In 1975, computer programming was taking off, and students at universities were learning to program on mainframe computers using Unix. And those students then went on to work at corporations and software companies and took their love of Unix with them. And since then, Unix has grown and improved. The first public version of Unix in 1975 is often referred to as System 5, but over time, more branches have been released, and that continues today. The most famous of these is probably the Berkeley Software Distribution, also just called BSD for short. There have been other versions which are either open source, closed source, or mixed source. BSD is the first open source version. Linux is open source and comes in many variations, such as Red Hat, CentOS, Debian, Ubuntu, Kali, Gentoo, and dozens of others. Several large software companies have their own closed source versions of Unix. It's proprietary. Sun came out with Solaris, which was then bought by Oracle. IBM has AIX, and Hewlett-Packard has HPUX. Apple's Mac OS is considered mixed source, a mixture of open source software and closed source software. It's BSD Unix with additional code developed by Next, a company that was started by Steve Jobs and then purchased by Apple. Apple's branded this combination Darwin. So Unix today really means a Unix-like system. Different versions of it have different quirks and peculiarities, but they all work according to the same fundamental principles. And it's become very common. You'll find it in iOS, inside iPhones and iPads, and in Android, in phones and tablets. They all run Unix too. So even though it was originally created 50 years ago, Unix still powers the devices that are around us in our everyday lives. Let's discuss the different ways that we can access Unix. I doubt that many of you have a mainframe at your house. We also don't have to do it the old way of sending a letter to AT&T so that they'll send us a copy of Unix. Instead, there are a few different options that are easily available. The first is that if you have a Mac OS desktop computer or a laptop computer, it's going to have Unix already built in. And you'll access it by going to the application directory, to utilities, and running a program called Terminal. If you have a Linux computer, the program will also be called Terminal, and you can get there from your desktop's application menu. If you're on Windows, you can also run Linux, but you'll need to install a little extra software to do it. It's called Windows Subsystem for Linux, or WSL for short. You can install it from the Microsoft Store, and the Microsoft website includes instructions for installing it for different versions of Windows. A fourth option is that you can sign up for a Linux server. There's a number of companies out there that provide hosting options where you can sign up and be given a Linux server that you can then log into and work remotely. They do cost money, but some of the plans are as low as $5 a month. If you're a web developer who's planning on putting your code online, it might be a good option for you. When we use Linux, we're going to be using it directly from the command line. That's different than the graphical user interface that you may be used to using on computers. The reason that we're going to be using the command line is we're going to gain more power and control by doing it that way. Having a graphical user interface is very convenient. It's very friendly, it's easy to move around the file system, and it's great for using with programs like Photoshop, where you want to be able to use your mouse to interact with an image on the screen. But when we're working with data and code, sometimes those non-data elements can get in the way. I often think of it as being similar to the difference between car transmissions. If you have an automatic transmission in your car, you give up some amount of control for having convenience. You don't have to worry about shifting gears, the car does it for you. But you're not necessarily getting the best shifting possible when you do that. With a manual transmission, you give up some amount of convenience, but instead you get control. So essentially what we're going to be doing in this training title is learning to drive stick. And like driving a stick shift car, most of the material in this course can be used with any flavor of Unix. Some commands may differ slightly with some of the options, but generally they work the same, and you'll be able to quickly adapt to any Unix system. I'm going to be using a Mac for this course, and to get to that command line program, I'm going to go to the Utilities folder. Again, that's going to be Applications and Utilities, or I can use the Go menu to choose Utilities or the shortcut that it gives me. Once I open that up, you'll see that there's a program here called Terminal that I can double-click to launch. I use Terminal so frequently that I usually have a shortcut for it down in my dock. Whichever way you decide to access Unix, once you get to that command line, you should be able to follow right along with me. In this movie, we'll talk about what it means to log into Unix and begin to learn to use the command line. When I launched the Terminal application, it opened a window that has a prompt in it waiting for me to type commands. Your window may look different than mine. It is configurable. I can go to the Terminal Preferences to change the way that mine looks. In the preferences, I can set the background, the text size, the color, and more. Old Unix systems were usually green or yellow text on a black background, and I still prefer that. I think it's easier on the eyes and easier to read. The window has a prompt right here. That's that cursor waiting for me to give it some kind of input. The text of your prompt will be different than mine. It's configurable, and different versions of Unix have different default settings. Yours may be showing your username, the current directory, or the date and time, or something else. We're going to learn to configure the text of the prompt later on in this course, but for now, I've set mine to something simple, my initials followed by a $sign. Notice that the window reported the last login time at the top. Every time I open a new terminal window, it's logging into Unix as a new session. And we can have several sessions open at once. I can go up to the terminal menu and choose New Window, or I can use the shortcut Command N. Now I have 3 different windows open, and each one is an independent connection to Unix. Now on a desktop, you're automatically logged in with your normal user account. If you connected to a remote server where more than one user can log in at the same time, then you would need to provide your username and password in order to log in. You can type the command who am I, and it will tell you the username that you're logged in as. Now it's important to remember that Unix was designed to be a multi-user operating system. So each of these windows is a separate Unix login, but all using the same username. You can go into each one and type who am I, but we can also just type the command who and hit return, and you'll see that it reports a list of all of the currently logged in users. It reports that there's 4. The TTYS are the 3 windows that you have open, and the one at the top that's console is the overall GUI version of the operating system. It's logged into Unix too. It can be useful to have several windows open at once. We can be doing different processes in different windows. Each one of them can be interacting with Unix on its own. We've already seen how to enter 2 commands, who am I and who. Let's try another one. We're going to use the echo command, and then in single quotes, I'm just going to type hello space world, and then another single quote. Now after I type the command, I'll hit return to signal that I'm done and that Unix should process the input. In this case, it runs the command. It does the action where it outputs the quoted text and then gives me another prompt. It's ready for more input. And it's the same thing we saw with the previous commands. Let's try another version. I'll do echo, and let's do Unix is great in single quotes. And you'll see that it echoes back different text. It's the same command in each case, but we're giving it something different to output back to us. One useful tool is that you can use the up and down arrows to move through the history of previous commands. So if I hit the up arrow once, I see the previous command, Unix is great. If I hit it a second time, it goes back to echo hello world. A third time, it goes back to who, and then to who am I. And the down arrow will move back down those commands as well. So we can navigate our previous command history. It's very helpful, and I'm going to be using it a lot to save typing. Let's pick one of those past commands, and let's make an edit to it. I can use the left and right arrows to move along the line. So here you can see I'm moving my cursor back and forth, and right after Unix is great, I'll add an exclamation point. Now from anywhere in this line, I can hit return, and it will tell Unix that it should go ahead and execute that command. I don't have to be at the end of the line to do that. It's very useful to be able to go back to previous commands and make minor adjustments to them. There's some other useful shortcuts for working with the command line. As we just saw, you can use the up and down arrows to review previous commands. The left and right arrows move along the current input line. You can also use Control plus the A key to move your cursor to the start of a line. So just immediately move all the way to the beginning of the line. That's very useful when you want to make a change at the beginning of the line. You don't have to just hold down the left arrow till you get there. And similarly, you can use Control plus E to quickly move your cursor to the end of the line. So maybe you've gone and made a change somewhere in the line, and now you want to jump to the end and make another change. You can do that with Control E. Tab is a very useful helper. Anytime you're typing a command, you can type tab, and Unix will try to guess what command you mean or what file name you might be trying to write. We'll be using that a lot, so you'll see how it works. And then last of all, if you want to clear your screen, you can type the clear command, or on some terminals, Command plus K, and that will clear the screen and the scroll back. So you can try some of these out. You can use the up arrow to go back to the previous line. Control A will take the cursor to the beginning. Control E will jump it back to the end. If you want to try using tab, you can type WH and then hit the tab. So now I have some suggestions I can choose from. Let's just choose who. And then once it's done completing that, let's try another one where we do HWOA. And now there's only one command that matches. It's who am I. So when I hit tab, it goes ahead and auto completes it for me. So you'll find the tab key to be very handy. When we're done using our Unix session, there are several ways that we can quit. The first is that we can type exit, and it will log us out of the session that we're currently working in. You'll see it says process completed at the end. Now there's nothing else that we can do. Hitting any command doesn't do anything. You can type on your keyboard all you want, and it doesn't take input. The second thing we can do is we can simply close one of these windows, and that logs us out as well. Or the last thing is you can choose the program itself and choose to quit out of terminal, and that will also log you out of Unix. In this movie, we'll discuss the structure of Unix commands. Commands in Unix have three parts. There's the command, then any options for the command, and then any arguments to the command. They're always in that order. The command is always a single word. It's the action that we want Unix to perform. We saw this in the previous movie with our first example where we used echo. After that, we didn't have any options. Options are optional. The argument is hello world. That's a text string, and it's inside quotes so that Unix knows that it's a single string of text. The options modify the behavior of the command in some way. If we had used the -in option with echo, it would suppress the new line return after the output. So there's the normal behavior for the command, the default behavior, and then there's the modified behavior using an option. Notice how the spaces separate the command, the option, and the argument. You may also have a command with an option that doesn't have any argument. For example, here I have the make command with the -v option. That reports the version of the command that we have installed. -v is a very common option. A variation on this option is -- version. It does the same thing. Options are usually either a single dash followed by a single letter or a double dash followed by a keyword. We can also have a list of several options. Here I have the ls command, and then the options L, A, and H, and then the argument /usr. That's going to point to a directory. We'll talk about those later on. You can also combine several options together, and the order doesn't matter. So this does the exact same thing. It applies the L, A, and H option to the ls command, but I'm just writing it in a more compact form. If I had used the option -HLA, it would also do the same thing. The order doesn't matter. You can't always combine these options together because sometimes options have their own arguments. Here, I have the -W option, and the argument for it is 50. Now, 50 is an argument for the option, not an argument for banner. The W option sets the width of the banner, and 50 is telling it how wide that banner ought to be. You may also see the option and its argument together without a space, which makes it a bit more clear which one is the option and which one is the argument to the command. A command may accept multiple arguments. Here, the cat command is going to concatenate two files together. The -in option numbers the lines in the output and could also be left out. I left it in mostly just as a placeholder visually so you'd see where the options are. Notice that there's two arguments. The first argument is file1.txt, and the second argument is file2.txt. The cat command will take 1, 2, 3, or more arguments, and it will just keep adding those files together, one after another. Let's try a couple of commands. For our first command, let's use the echo command again, and then we'll put a space, and then in double quotes, I'm going to write Unix rocks. Notice that I'm using double quotes here where I used single quotes previously. It doesn't make a difference. Both of them tell Unix that this is a string. I hit return and you can see what it does. Now we can hit the up arrow and use our left arrow to move back in the line to type a -in option in between, and you'll see that now we get a slightly different behavior. It doesn't have a line return at the end. When it outputs, it put a quirky character instead. So let's try another example using the ls command. We're going to be learning more about this later on. The ls command is going to list the contents of our directory. So you can see that its normal behavior looks like this. If I type ls and then a space and follow it with -l, -a, -h, it'll pass in the L, A, and H options, and you'll see that I get a very different set of output. It formats it in a different way. I could also hit the up arrow and change that to LAH, and you'll see I get the exact same output. It doesn't matter whether I separate those options or combine them together. And then let's use the clear command that we learned in the last movie to clear our screen. And let's now use banner with -W and then 50. And let's do Unix rocks. And you'll see that it makes a nice big banner there. If you want to scroll up with your mouse, it's oriented horizontally so that it's suitable for printing, which was especially useful when you had continuous feed printers. You could make very easy, inexpensive banners. So these are the fundamentals of using commands in Unix. Just remember that it's always the command, followed by the options, followed by the arguments, in that order. In this movie, we'll learn about kernels and shells, which are an important aspect of the Unix operating environment. The kernel is the core of the operating system in Unix. It's the part that's responsible for allocating time and memory to each program. It does the fundamental management of how commands and programs conduct their work. You aren't going to need to worry about choosing a kernel. You made that choice already when you picked a version of Unix to use. Different versions have different kernels. The shell is the outer layer of the operating system. It's what we see when we open up a terminal window. We're working in the shell. It interacts with the user, and we can think of it as our working environment. The shell will send requests to the kernel. The kernel will then do its job and launch programs, and then the results will be returned back to the shell so that we can interact with them again. We do have the ability to choose different shells. They're all similar, but they have some slightly different features. The very first shell was called SH. It's also known as the Thomson shell because it was created by Ken Thomson. It was the primary working environment for a long time. Then, in 1977, the Bourne shell was created by Stephen Bourne as a replacement for the Thomson shell. Notice that it has the exact same name, SH, short for shell. Then it starts to become more common to have choices about which shell you use. You'll notice that a lot of the names have a bit of programmer humor in them, starting with the C shell, or CSH. Then there was the TCSH, the tabbed C shell, the KSH, or corn shell, and the bash shell, which is the born again shell. You can see how that name is a play off of the Bourne shell. The bash shell has been one of the most popular shells for the last 30 years, and it's often the default shell. It's the one that I learned on and the one that I used for many, many years, until recently I started using the Z shell instead. One of the most notable recent shells is the fish shell, or friendly interactive shell. There are many shells besides these. Dozens and dozens of them. They all work in a very similar way. They're just trying to improve on the shells of the past. It's also possible to switch shells while you're working, and for different users on a multi-user system to each pick the shell that they like best. It's a lot like picking a favorite flavor of ice cream. For beginners, the difference between these shells is small. A lot of the difference between them is going to be the features that are available to high-end users for tasks like advanced shell scripting. For now, you can safely stick with whatever your default shell is. Let's look at the command line. As I said, when we're inside one of these windows like this, we're inside the shell. That's the working environment that we're in. You can see actually that my window tells me up here that I'm using the Z shell, ZSH. We can see that this is my default shell if I type the command echo followed by a space and a $sign and then all capital SHELL. When you hit return, it tells you the location of the shell that you're currently using. You can see that it's ZSH. We also can type echo space $0 and it'll tell us our current shell. Again, it tells us ZSH. Now, the default shell and the current shell don't have to be the same. We can switch shells. For example, I can type the command bash and it will switch me into the bash shell. Now, on Mac OS, it comes up with an extra message that many of you may not see. That's because the bash shell was the default Mac shell for a long time, and it has recently switched to the Z shell. So this is a message just to let users know about this change. The message is not important. What I want you to see, though, is that if I type echo space $0, it now tells me that I'm using the bash shell. I'm inside the bash shell, and whatever quirks and peculiarities it has, that's now my working environment. Let's also, from here, go into KSH. Now I'm in the corn shell, or KSH. Echo $0 will tell me that. I can do TCSH. You can see that my prompt changed when I did that. I can do CSH, and now I'm in the C shell, or I can do SH, and I'm all the way back in that Bourne shell. Now, each time I type one of these commands, I'm actually moving into a shell within a shell. They're like layers. So right now I'm actually working inside the Bourne shell, inside the C shell, inside the TC shell, inside the corn shell, inside the bash shell, which is inside the Z shell. I'm several layers deep. It's a bit like Inception, going one layer deeper each time. So if I type exit now, it doesn't exit out of the program, it exits out of the shell. If I type exit again, I go back another level and back another level. Let's just stop and take a look and see what level we're at. I'm at KSH. I can exit again, and again. And now if I do echo $0, you can see I'm back at that ZSH shell. That dash at the beginning is an indicator that I'm back at the very root. As I said before, you're probably going to stick with your default shell throughout this tutorial, whatever that may be. What I want you to understand is that the shell exists, that it's the working environment that you're in, that different users can have different default shells, and that you can change shells if you need to. In this movie, we will look at some of the text editors available for Unix. Unix has been around a long time, even before modern code editors that have graphical user interfaces. Instead, we have text editors from the command line. The very first text editor was called ed, short for edit text. It was very simple, but not user-friendly. The VI text editor was a big improvement. It allowed viewing and editing a whole document at once. VI is short for visual editor. VI was further improved and replaced with Vim. If you try to use VI, chances are it will open Vim instead. Vim is still in use, and many Unix users prefer it. One key feature is that your fingers get to stay in the center of your keyboard. The same keys perform a variety of actions by switching into different modes: normal mode, insert mode, visual mode, and so on. It can be efficient, but it's tough for beginners because you have to get used to switching between those different modes. Another popular editor is Emacs. It stands for Editor Macros. Its power comes from the macros that can perform complex tasks. You can think of it as being a Swiss Army knife. It's powerful, but it's difficult for beginners who don't know how to use its macros. A better choice for beginners is Pico, which later became Nano. Pico stands for Pine Composer. Pine was a very simple email program on Unix that would allow you to send emails from the command line. Users would compose an email message using Pine and then send the message. Pico became a standalone text editor that worked the same way. It was improved and replaced with Nano. The name Nano is a play off of Pico. Pico is a size prefix, and Nano is 1,000 times larger than Pico. In most cases, Nano has completely replaced Pico, and if you try to run Pico, you'll end up in Nano anyway. Nano has a basic feature set, but it's very easy to use. Let's try it out. From the command line, we're going to just type NaNo for Nano, and then hit return, and it'll drop us into the Nano text editor. You can see that we still have a cursor here, and it's ready for us to type some text. So this is some text. I can hit return to go to a new line. I can type a bit, and then I can hit the delete key to erase. I can also use the arrow keys to move around. This is more text, and then I'll just use the arrow. I can hit the up arrow and the down arrow. On some operating systems, you're able to hold down a modifier key like Option and click for the spot that you want it to jump the cursor to. But that's not always true. Many times you'll need to use the arrows to move around. You can see that it works a lot like a text editor, and I can insert text or change text in the way that we would expect. Notice that there's a menu of commands at the bottom of the screen. Each one of them is preceded by the key combination we have to enter in order to get that command to run. The up arrow or caret that you see in front of those letters is the control key. So if we type Control G, it will do the get help command. We can try that now. Control G, and I'm now in Nano's help text. I can use the arrows in here to move around up and down, or I could also enter the commands for next page and previous page, which you see down there. You'll see that there's a command for exit, Control X, and that will exit back out of it, back to the text editor. We're not going to go through all those commands there. You can explore on your own, but I'm going to use the Control X in order to exit out of Nano. When I do, it's going to come up and ask me if I want to save the modified buffer. That's essentially asking me if I want to save my changes. It's similar to the pop-up window that you would get if you tried to close a Microsoft Word file without saving your changes first. If I type yes, then it's going to ask me for the name of a file to save it to. But I'm not going to do that. Instead, I'm going to type in for no, and it will throw away my changes. If we want to start a new file, that's a great way to do it. If we want to edit an existing file, we can type nano and then just provide the file name as the argument to nano, and that's the file that would open up for us. You may wonder about using other text editors instead. You can really use any editor that saves content only as text. That's what we're going to be working with in Unix, is going to be text. So that means you can use code editors that you might be familiar with. Visual Studio, Atom, Sublime, Notepad++, Nova, all of those would work and be able to save information as text so we can work with it in Unix. You would not want to use word processors because those are going to store style information that's intended for display in a graphical user interface, which is not what Unix is. But since we're focused on Unix, in this course we're going to stay away from code editors and instead stay inside the command line and become familiar with the editing tools that Unix gives us. In this chapter, we will learn about the Unix file system and how to work with files and directories. Let's begin by looking at the basics. In Unix, we can move between directories. It's similar to how you can navigate into different directories or folders in a graphical user interface. For example, I can open up a new window and I'm in my user home directory, and from there I can double-click on public and move into the public directory and double-click on Dropbox to move inside that directory. Each time I click, I change the directory that I'm in. The current directory in Unix is called the working directory, and the working directory is important because many Unix commands will operate based on that directory unless we tell them otherwise. For example, when I use the ls command, it's going to return a list of the contents of the working directory. When you first log in, Unix is going to set your working directory to be your user home directory, the same way that it did over here when I opened a new window. We can find out our current directory by typing the pwd command, that's short for present working directory. You can see that it returns a path to my home directory. You shouldn't be concerned if your path is different. Different versions of Linux handle it in different ways. What this is telling me is that I'm inside a directory called Kevin Skoglund, which is inside a directory called users, which is at the root of the hard drive volume, and we call this a path. Let's look at the files that are in the current directory. We already saw that we could use ls to get a simple list of them. We can use ls with the -l option to get that same list, but formatted differently. Notice that the far right column contains the same information. We just now see additional information as well. We'll be talking about what some of those other columns mean a bit later on. I'll go ahead and point out that the fifth column there, the one that comes right after staff, that column is the size of the file. And if we use ls-l with the h option added, it'll give us those sizes in human readable format. It'll tell us in terms of bytes, kilobytes, or gigabytes. That can be a lot easier to read. Another option we can use is the A option. This is for all, and this is going to show us all files that are in the directory, and that includes dot files. The convention in Unix is that if files begin with a period, they aren't shown by default. Often these are configuration files, either for the system to use or for programs to use. They're usually not documents or data that you want to work with on a daily basis. Using the -A option will show you those files as well. Notice also that those files start with a dash and not a D. The D is because this is a directory. This applications is a directory. We can see it over here as well in the graphical user interface. The D is letting us know it's a directory, whereas this above it is a file. There's one more thing I want to point out to you. If you scroll up or expand your window so that you can see the top of that list, the very top two entries are not actually files that are in that directory. The first one is a dot, and that's a representation of the current directory. This is a way for me to be able to see information about the current directory or to be able to address it in commands that I write. Dot dot is a representation of the parent directory. We already know from typing the pwd command that that is the users directory. So dot dot is a convention that always represents the directory that's right above this directory. That'll be important when we start moving around between directories. Let's try that now. Let's start by using the cd command to change directories. You're going to be using this command all the time when you're working with Unix. So I'll do cd space, and then I'll type the name of the directory that I want to move into. Let's go into that library directory. cd space library and hit return, and now I've moved to the new directory. If I type pwd now, you can see that the path has changed. My current working directory has changed. I can type ls inside that directory. You'll see that now I get a different listing of the files. I could also move into one of those, but what if I wanted to go backwards? In order to do that, we would use cd space and dot dot. That's where that dot dot convention helps us again. It allows us to go back to the parent directory And now you can see I've moved up one level. So I went into the library directory, and then I backed out of that directory. I can go into more than one directory at once by using library and then slash, and then let's go into preferences. Now I'm going to type pref, and I'm going to hit tab, and you'll see that it auto-completes that path for me. And you'll see that it starts to auto-complete the file for me. Now it didn't completely auto-complete it because you can see up above that there's two files that both start with the word preference. There's preference panes and preferences. If I hit tab twice, it'll come up and offer me the choice between those two. I'm going to choose preferences and then hit return. Now I do pwd, you can see that I've moved into that directory. If I want to go back more than one directory at a time, I can also do that with cd ... Now I've moved back to my user home directory again. So we can use these conventions to put paths together to move around. These paths are relative to the current directory. I can also do it relative to the root of the hard drive. We call that an absolute path. And to do that, I just need to put a / at the beginning. So / users and then / Kevin Skoglund and library would take me to the same place. But it does it by starting at the root of the hard drive and working forward from there. We can also always get back to our user home directory using cd space and then the tilde symbol. That's probably on the upper left-hand corner of your keyboard. That'll take me back to my user home directory. And another nice little trick is you can do cd space with a minus, and it'll take you back to the last directory you were in. So you can see I was in the library directory, I went back to my home directory, cd dash took me back to the directory I was in previously. The last thing I want to give you to orient you is a sense of what things are stored where in the Unix file system. There's a number of directories at the root of the hard drive that are common for Unix installations. The first is bin, and that's typically where commands and programs are stored. There's etc, which some people pronounce etc, and some people pronounce etc. That's where your configuration files go. Next, we have the home directory. That's the place where historically user home directories were stored. That's often still the case on Linux systems. On Mac OS, they're somewhere different, but home is where you would expect to find home directories. And lib is where system libraries go. Temp is a place for temporary files. USR is for Unix system resources. Those are files that the operating system needs to use. And then var is a place for variable system data files, which are a bit like temporary files, but they're things that the operating system uses and manages. Most of the time, you're going to be working inside your user home directory, but it is useful to know where Unix stores some of these other pieces in case you ever need them. Now that we have the basics of the file system, let's start working with files and directories. In this movie, we'll learn to create files in Unix, and we'll do that using the nano text editor that we talked about in the last chapter. Before we do, let's start by looking at some of the best practices for naming files in Unix. Unix file names have a 255 character maximum. That's very long and more than enough for your needs. You can use uppercase and lowercase letters, numbers, underscore, hyphen, or period in the file name. You typically want to avoid using symbols. File names are case sensitive, so something like my file with a capital M and a capital F is different from my file, all lowercase. For that reason, most Unix developers prefer using lowercase all the time. For one thing, it's just less typing if you don't have to hit the shift key. They also prefer underscores over spaces. You can use spaces in file names. If you do, though, you have to escape them with a backslash, which again is just a bit more typing. You can also put quotes around file names if they have spaces in them, because you'll remember that in Unix, the space is a way that we can tell the difference between the command and the options and the arguments. So we have to make sure that it understands what is a space that's meant to separate those things and what is a space that's inside the file name. Most Unix developers avoid it altogether by using underscores. File endings that go at the end of files to tell you what's inside of them are not required by Unix. That's a later convention that grew up with other operating systems. But they are still helpful, and I would recommend still using them. For example, if I create a text file, I go ahead and put .txt at the end of it. Let's try a couple of examples of creating a new file. Let's start by just using the nano text editor. So I'll type nano and I'll hit return. Now I'm inside that text editor. This is my first file. I'll type some text inside of it. And then in order to save it, I just need to exit out. So Control X will exit, it'll ask me if I want to save my changes. Before I said no, but this time I do want to save them. So I'll type Y. It says, what file name do you want to write it to? Now I need to use those naming rules that we just talked about and give it a file name. So I'm going to call it first_file.txt. That's a good name. It has an underscore instead of a space. It's a little hard to see there. And I'm using that file extension at the end. It's all lowercase. I'll hit return, and it created the file for me. How do I know that it's there? Well, I can type ls, and I can see it, first_file.txt. Notice that I was in my home directory when I created it, so that is where it put the file. It assumed that I wanted to put it in the current working directory. That's why it's important to understand what directory you're in. It's going to decide where these files end up going. Now, if we want to reopen that file to make changes, we can type nano space first, and I can hit the tab, and it'll go ahead and auto-complete it for me. I hit return. This is my first file. It is a good one, and I'll hit Control X, and this time it'll say, do you want to save your changes? And I'll say yes again. It offers me the chance to change the file name if I want to create a new file, right? Leave the old file alone, but save this as a different version, maybe V2. I could do that. Instead, I'll hit return, and we'll just update the existing file. I also can type nano with a file name that doesn't exist yet, and it will go ahead and create that file with the idea that that's going to be the name. See, it puts that up there at the top. This is my second file, and I'll use Control X to exit, yes to save the changes, and notice that it already pre-filled the file name to write as secondfile.txt. It's a very similar kind of workflow. If we know what the file name is going to be at the beginning, we can go ahead and offer it, but if not, that's okay. We can just use nano and choose the file name later. That's how we can create files in Unix using the nano text editor. In this movie, we're going to learn how to read content from files. There's three main ways. A fourth if you count opening up inside a text editor, but we're not going to do that. We're interested in commands that will read files for us. The first command is called cat, and it's kind of a funny name. It's actually short for concatenate. If we give cat several arguments, it'll read the files and also concatenate them together. But if we give it only one file name, well, then it will just return the contents of that file. So it becomes the de facto way on Unix to just look at the contents of a file. You cat and then the file name, and you see what's inside the file, even though it's not actually doing any concatenation. That works really well with short files, but if we have really long files, we'd really like to have some way to view those in pages or sections instead of having it just all output at once. I mean, we might be viewing a file that has 5,000 lines in it. That would just scroll past very quickly. So we can use the command more in order to get paginated output. Now, more was the original Unix command, but it's since been replaced with something called less. It's a bit of a programmer joke. Less includes backward scrolling and better memory use. It's a joke because less is now greater than more. On most modern Unix systems, if you ask for more, you're very likely going to get less in return. Let's try these out. In order to have a long file to work with, I've included in the exercise files something called lorem-ipsum.txt, and it just has a bunch of lorem ipsum text so that we have a long bit of content to look at. We don't know how to copy and move files yet, so for now, let's just open up a new graphical user interface file, and let's just drag lorem ipsum into the same directory where we have first file and second file. Now when I come back over here and I type ls, we should see it in our directory, and there it is right there. So let's start by using cat, and let's just do cat with firstfile.txt. I can use tab to autocomplete the name, and you see it just outputs the contents of that file. Nice and simple. If we do it with the second file, cat secondfile.txt, you can see it outputs those contents. And if I do them together, first file and then second file, you can see that it just concatenates them together one after another. That'll be a useful feature once we start learning how to direct output because we can merge files together this way. For now, let's look at cat with lorem ipsum, and you'll see what the problem is. I'll hit return, and there it went. It just zipped right past me. Now, we certainly could go and use our terminal to scroll back up to all of that, but instead, a better approach, let me clear the screen here. Instead, a better approach is to use less. So I'll use less with lorem ipsum.txt, When I hit return, it'll now take me into a viewer starting with the first page. You'll see it starts out with lorem ipsum dolor sit emet. That's at the very top. And then it's waiting for me to do something. I can use the up and down arrows to move up and down the text. Or even better, I can use the space or the F key to go to the next page. Most developers, I think, use the space key. So now I'm looking at the next page, and then the next page, and the next page. And it's a very convenient way to move through the pages of the document. B will take me back a page, so it's F for forward and B for back. You also have the H command to bring up a help menu that shows you all the commands. It says press Q when done, so I'll press Q. And also when we want to exit out of this, when we're finally done looking at our file, we can type Q again there. So it's extremely common in Unix to use cat and less to view file contents. Before we leave this and move on, I want to show you one other thing. If we type pwd to find out our working directory, and we know what files are in that directory, I want to show you that you can address these files in several different ways. We used cat with firstfile.txt to view it, but we also could go in front of that and put our user directory. We can say go to our home directory and look for a file called firstfile.txt, and it returns the same file. Or, as we already saw, we could do an absolute path with users Kevin Skoglund firstfile.txt, and it will return it to us. Or if we had moved to our library directory and we wanted to look at the file that was in our parent directory, we could use cat with / firstfile.txt. Notice the autocomplete is still able to figure out where these files are located, so hitting the tab still works. So it'll output it that way too. So there are a number of ways that we can find the files that we're looking for in order to read them or to tell Unix to work with them. We can navigate to the directory where they are and access them that way, or we can provide a path to the file, either an absolute or a relative path to our current working directory. Now that we know how to create files in Unix, let's learn how to create directories. The first thing you need to know is that the directories that we get to from the Unix shell are the same as what we access from the graphical user interface. So for example, if we do ls, we see a list of the different files and directories that are in the home directory. And then I go to the graphical user interface, we see those same files and directories are here. That means that I could easily create a new directory using new folder or whatever your operating system uses to create a new folder or directory in the graphical user interface, and it will then show up here in the listing inside Unix. They're exactly the same. But we can also create directories from inside Unix, and we can do that with the mkdir command. That's short for make directory. mkdir space, and then the path to the directory we want to create. By default, it's going to be in the current working directory. So if I use my_project, now it will create a directory inside the current directory called my_project. Let's use ls and then space -l to get a listing, and you'll see that it created my project, and you'll see that it is a directory. It has a D in front of it. Let's try making that same directory again, my_project, and you'll see that it already exists. So it won't let us create a directory if one already exists. This creates a directory in the current working directory, but we can also provide a path somewhere else. For example, we could do make dir and then my_project and then junk, and that'll make a directory inside the my project directory called junk. If we do ls and my_project after it, it'll list the contents of the my project directory, and you see the directory there called junk. Let's go up and just add the -l option, and we can see that it's a directory. Now I want to share with you a useful trick. Let's say that we want to create two nested directories. For example, let's say we wanted to make dir and then use the my project directory, but inside there, we know there's only one directory right now called junk. Let's create a new directory called test1, and inside there, another directory called test2. If we hit return, it's going to say, sorry, I can't do that because test1 doesn't exist. That's probably what you would expect to happen, right? We need to create test1, and then we could create test2 inside of it. But a nice trick is that you can use the -p option, and you can create them all at once. Now, if I do ls-l for my project, you can see it has test1. And if I then look inside test1, it has test2. It doesn't complain anymore. It just creates all of the parent directories that it needs on the way to creating that child directory. So that's how you create directories in Unix. You use the make dir command, you provide a path to the directory can't already exist, and if some directories in the path to that directory don't exist, you can add the -p option to create those parent directories at the same time. Let's learn how to move and rename files and directories in Unix. In the graphical user interface of an operating system, we usually use the mouse to drag files and folders around. But in Unix, we'll use commands. I'm going to start out in my user home directory, and I'll type ls so we can see what files and directories are already there. And you can see that we created these files before: first file.txt, we have lorem ipsum.txt, my project, and second file.txt. Those are the ones we're going to be working with here. Let's start by moving first file.txt into the my project directory. The way that we'll do that is with the mv command for move. So we're going to move, and then the second thing is the target. What do we want to move? Well, we want to move first underscore file.txt. Notice that I hit the tab key to have it autocomplete. Where do we want to move that target to? Well, we want to move it into my underscore project / first file.txt. That's its new location. The move command will accept any path for a target and any path for its destination. I'll hit return, and now let's type ls again, and you'll see that first file has left this directory, and instead, if I do ls my project, you'll see that it's now inside the my project directory. We moved it into that directory. Let's also try moving that lorem ipsum file. mv lorem ipsum, and this time I'm going to put it in my project folder, but I'm not going to type the name of the file again. Before, I told it I was moving first file to this destination, and I gave it everything all the way down to the file name. Now I'm just going to give it a directory. So I'm essentially telling it move a file into a directory. And once again, I'll hit the up arrow, and you'll see that it moved it in there. So you don't have to specify the file name again if it's not going to change and if you're putting it into a directory. Now we're ready to talk about renaming, because it works exactly the same way. In fact, it's still the mv command. Moving and renaming are the same thing in Unix. We're moving it from one location to a new location with a new name. So in that first example, where I provided the full file name, I could just provide a different file name instead. Let's try that with second file. Let's type ls so we see what's in this directory. There's second file. So I'm going to say mv, and the target will be second file.txt. Let's move it into my project, but this time, let's don't say that the name is the same. Let's say the name will be different. I'll make it file underscore second.txt. I'm flipping those names around. Now, when I type ls, you'll see it moved. ls for my project tells me that it's in the new location, and notice it has its new name. So that's all there is to renaming. Renaming and moving are the same thing in Unix. Let's navigate into our project now that all of our files are in there. I'll type in ls so we can see the contents again. So now let's just try renaming first file to match that same pattern we did for second file. So I'm going to move first underscore file.txt to file underscore first.txt. Notice I'm keeping them in the same directory. I'm not putting it in a different directory. I'm not moving it somewhere else. I'm just renaming it in place. Now when I type in ls, you'll see that we have file first and file second. Now this is moving files around, but directories work the same way. Let's type ls-l just so we can be clear on what the directories are here. I have a directory called junk. You can see the D here, and I've got another one down here called test1. If we look inside test1, ls-l, test1, you'll see that there's another directory inside it called test2. Let's move that test2 directory out of the test1 directory. We can do that with mv, and then the path to the target, which is test1/test2, that's our target. And then where do I want to move it to? Well, I want to move it to the current directory. We learned earlier that the current directory is symbolized by just a single period. Remember, the parent directory is a double period. A single one by itself is the current directory. So now I can type ls, and you'll see that it has moved the test2 directory back a level. I'll hit the up arrow a couple times. We'll see what's inside test1, and you'll see now it's empty. There's nothing in there. And you can rename directories the same way. Let's make the junk directory renamed into all_junk. And now when I type ls, you'll see it's over here, and it's called all junk. There are a couple of options to the mv command that you need to know about. The first is the -f option, which will force it to overwrite a file. So if you move one file to the position where another file already exists, it would overwrite that other file. Now here's a very important thing. That's the default behavior. So if you had a file called report.txt and you moved another file and renamed it to report.txt, it would overwrite the first one. It would be gone forever. You can use the in option instead if you want to make sure that you don't overwrite a file by accident. Or there's the -i option, which is interactive. If it's going to overwrite an existing file, it'll pop up and ask you what you want to do. Let's learn how to copy files and directories in Unix. Just like we did with move, we're going to be doing that from the command line. In the last movie, we moved a lot of our files into the My Project directory. If I type ls-l, we'll see what those are. You can see I've got several files that are in here, as well as a couple of directories. Let's start by trying to copy this file right here, filesecond.txt. The way we're going to do that is with the cp command, short for copy. Just like we had mv for move, we have cp for copy. We'll use a space, and then we'll take any path to the target that we want to copy. The file we want is in the current working directory, so we can just type its name, file_second.txt, but we could easily provide a path to a file that was somewhere else, either an absolute path or a relative path. And then we want to put the target. Where do we want to copy this file to? Again, it can take a path anywhere on the hard drive, but we're going to put it in the current working directory. So let's just call it file_third.txt. I'll hit return. Now, if I type ls-l, you'll see that I have two files, filesecond.txt, filethird.txt, and they have the same number of bytes in them. Both have 25. If I cat file second and cat file third, you'll see that they have the exact same information inside of them. So that's how we copy a file. What about copying a directory? Let's take our test2 directory and let's copy that. I'll use cp again, and then the path to it, which is test2, and the path to what we want to create, I'll call test3. Notice now it didn't do it for me. It came up and complained and said, what you've given me as a target is a directory, so I haven't copied it. This is a good fail-safe method built into Unix. For us, it's very obvious that this is a file because it has a file extension at the end. But remember that extension is not required in Unix. We could just as easily have a file called test1 or test2. Because of this, it's not always obvious what's a file and what's a directory. So rather than accidentally copy tons of information that you don't mean to, Unix comes up with a warning instead. And if you want to copy a directory, you have to provide an option to copy. So you use cp space and then -R. That's the option. And then the rest is the same. That R is for recursive. So it will recursively copy test2. What that means is it will copy the test2 directory and all the files that are inside test2 and any directories that are inside test2, plus the contents of those directories, which may contain other directories, which may contain other directories, and so on. And it will recursively copy all of them down the line. We'll hit return, and you'll see that it works. ls-l, and now we have test3. Now that directory was empty, so there was nothing in it. Let's try putting something in it and try copying again. Let's move test3 into test2. We learned how to do that in the last movie. And then let's also move file third into test2, test3. We can use our move skills for that. Now, if we look at ls-l, we'll see we just have test2. If I now look inside that directory, it has test3, and inside there is filethird.txt. So we have a few things that are nested inside there. So when we go to copy those recursively, cp-R test2, and this time let's call it test2_backup. It's the kind of thing you might do. You want to back up a directory. you could just tell it to copy the entire directory so we have a pristine backup to keep track of. I'll hit return. And now when we do ls-l, you can see there's test2 backup, ls-l test2 backup. There we go. Contains test3, and that contains the file third also. So it copied all of them recursively. In addition to the recursive copying option, there are a couple of other options for copy, and they're the same options that we saw for move, but they work a little bit different. So we have F, N, and I. F is for force overwriting. The difference here is that instead of being the default that it will always overwrite, like it was with move, instead it will only overwrite if the directory that you're copying is empty. So let's say you had a directory called vacation photos, and it was empty, and then you took something else and you copied it to the location vacation photos, it would overwrite the blank one with whatever you were copying. But if there were already photos in that vacation photos directory, it would not. It would refuse to do it without you providing the -F option to force it to do it. And then just like we saw with move, N is for no overwriting and I is for interactive overwriting. By far and away, the one you're going to use most is that capital R option. Now that we know how to create, move, and copy files and directories, let's learn how to delete them in Unix. The first and most important thing you need to know is that deleting in Unix is not the same as putting items in the trash or the recycling bin on your operating system. The trash can was a later user-friendly invention. On Unix, when you delete a file or folder, it is gone immediately and forever. You can't move it back out of the trash. It's gone permanently. Let's go to the command line and try deleting some files and directories. Notice that I'm inside the My Project directory, which is inside my user home directory. Let's start by doing ls-l so we can see what files and directories are there. Let's create a duplicate of file second.txt, and then we'll delete it. We learned how to use copy in the last movie, so we'll do file_second.txt, and the new file is called deleteme.txt. I'll do ls-l again so we can see the file is there. Now we're ready to delete it. To do that, we're going to use the rm command for remove. So we have mv for move, cp for copy, and rm for remove. After that, I can provide a path to the file or directory that we want to delete. In this case, it's a file that's in my current working directory, so I'll just type deleteme.txt. Then I'll hit return. ls-l again will show that the file has been deleted. Now, it is permanently gone. It didn't move it to some trash can somewhere that we can go and get that file back out again. It has been permanently deleted. Now let's try deleting with a directory. We have this directory test2_backup that we'll delete. It has a couple of items inside of it. We'll do the same thing with test2_backup. I'll hit return, but this time it doesn't work. And it doesn't work because it's a directory. Remember, it can be a little bit tricky in Unix to tell whether something is a file or directory by looking at the name. So as a result, Unix errs on the side of caution. It doesn't want us to delete too much accidentally. So when we're trying to delete a directory, it wants some extra confirmation from us that that's what we intend to do. To do that, we'll use the capital R option that we used with copy. So rm --R and then test2_backup. Now, it will happily delete the entire directory and anything that might have been inside of it. So if I do ls-l, you can see that that directory is gone. So rm and rmr are pretty easy to use, but they're very powerful and they're permanent. So be careful. You can easily delete a lot more than you intend. You could accidentally delete a database or a directory full of images by mistake. So use it with caution. In this movie, we're going to learn about something called symbolic links. Symbolic links are also called symlinks for short, and they're similar to the shortcuts or aliases that you might have used before in a graphical user interface. The idea is that we create an object that refers to an object somewhere else in the file system. The way that we create a symlink in Unix is with the ln command, ln short for link. It's very important that you use the -s option with ln. That's what creates the symbolic link. If you leave that off, it creates something called a hard link, and that works very differently, and it's rarely used. So rarely that we're not even going to talk about it here. we're just going to focus on the much more common and much more useful symbolic links. So ln with the -s option, followed by a path to the target file, and then the path to the symlink that we want to create. There's one very important difference between a symbolic link and the shortcuts and aliases that you might be used to. A symlink references a file path, not a file. It's literally telling Unix, hey, whenever I access this symlink, you should treat it as if I had given you this file path instead. Why that makes a difference is that the symlink breaks if the file is moved or deleted. It doesn't assume that the file is necessarily going to be in that place. That's very different from shortcuts and aliases, where the operating system adjusts them as files move around. Symlinks don't work that way. They're just a reference to a path. Let's try creating a symlink. I'm inside the my_project directory. ls-l will show us the files and directories that are already there. Let's create a symlink for file_first.txt. So we'll do that with ln space -s, and then the path to the target. In this case, it's in the current working directory, and it's just file_first, and then the path to the symbolic link. Now we could put this symbolic link somewhere else if we wanted to put it in another directory. I'm going to put it in the current working directory as well, just for simplicity. And I'm going to give it a very obvious name. I'm going to call it symlink. Now when I do ls-l, we'll see that our symlink shows up. Here it is. Notice that it has an arrow after it, pointing to the file path that it references. It's not a copy, and you can see that because the number of bytes that it uses are different between each one. If we type cat file_first, we can see the contents of the file. If you do cat symlink, you'll see it's exactly the same. We can also create symlinks to directories. That can be very useful. Let's take a look. We have our test2 directory, and if we do ls-l of that directory, you'll see that we have a test3 directory that's inside of there, and inside of that is a file called file_third.txt. Let's symlink this test3 directory into the current working directory. We'll do it with ln-s, and then the path to the target, which is test2/test3, and then the path to the symlink that we want to create. We're going to do that in our current directory. Let's go ahead and just call it test3. I'll hit return. We'll do ls-l. And now you can see, here's my symlink from test3, and it's symlinked to this path, inside test2 to test3. And if I were to read files from there, or move files into it, or even if I change directories into test3, it actually does move me into that directory. ls-l, and you'll see there's that file_third.txt. Now when I type pwd, the path that it gives me includes that symlink as to how I got there. It doesn't expand the path, right? This is effectively the same as this, but pwd goes ahead and puts in the path that I used to get there. You can remove symlinks just like you can files and directories, but only this symlink will be deleted. The original file will still be there. I'll give you a quick example of where symlinks can be useful. Let's imagine that we have a project that we're going to deploy, and that project has different versions over time. We can have a folder of releases that contain each of those versions, and each one of those folders can have a date. So we have a full project stored in 2021-01-01, another full project stored in 2021-01-14, and so on. We can create a symlink called current, which points to the current release. The other releases are still on the system, but we can tell our web server or whatever we're working with that it can go to current to find the latest release. And then when a new release comes out, we upload that. As soon as it's completely uploaded and ready to go, we can just adjust the symlink for current so that it points to the new version. And now we still have the old version there, but we've now deployed a new version of our code. And if there's a problem and we need to go back to another version, it's no big deal. We can just change the symlink and roll it back to use 0204 again. Symlinks are going to be a useful tool for you while working with Unix. Let's talk about how you can search for files and directories that you've created on Unix. The way that we search for files and directories is with the find command. The format is the find command followed by the path that we want to search. So we're going to search all files and directories inside that path. And then last, the expression that we want to use for searching. And there's a variety of expressions we can use. We're just going to be using the most common and most basic one, which is the name expression. So here I have the find command. I'm telling it to search in the root of the hard drive. That's what that / is. In the directory home, and in there, look for things where the name is equal to vacation_photo.jpg. And it'll look throughout that directory to see if it can find a file that has that matching name. The double quotes are optional, but I think they're a good idea. This type of expression is useful when you're looking for an exact file name, but what if you're not completely sure about the file name that you want, or you want to return several different files that match a pattern? Find allows us to use a couple of wildcard characters. We have the asterisk, which represents 0 or more characters. That's sometimes called the glob. Then there's the question mark, which represents any one character. And then you can put characters in square brackets to be a set. So any character that's in that set of characters. Let's try some examples so you'll see how to use these. Now you can see the path. I'm already inside my project. Let's start by typing ls-l so we can see a list of what's there. Let's say that we wanted to find that file that's called file_first.txt. We can do that with find and then the path that we want to search. You could provide that path a couple of different ways. We could provide the full absolute path that's up here, or we could search our current user directory by using the tilde, the little squiggly line that's a placeholder for it, or we could use the period, which says the current directory. I'm going to use that one. So find for the current directory, and in the current directory, I'm looking for something whose name, the single dash in front of it, is equal to file_first.txt. And there it is. It found it for me, and it returns the path to that file. Whenever you do a find, it returns the path that it takes to get to each of those files. And it'll return all matches. Let's see another example. We'll just hit the up arrow, but this time, instead of file_first.txt, let's put that wildcard in there. We'll use the asterisk. So it's going to find anything that ends in .txt. Now you can see it returned back file_first.txt. It also later returned file_second and lorem ipsum, which are in the same directory, but it even went into the test2 directory, into the test3 directory, and found file_third.txt. So I now see all the text files that exist in the current directory, no matter how deeply nested they may be. Let's try another example. We'll do this one with the question marks. Let's say we want all files that are F followed by 3 characters, and the underscore, and then the asterisk. So F, 3 characters, an underscore, and then some other text ending in .txt. You'll see that it comes back with those 3 file first, file second, and file third. Let's try one last example. We'll take away the question marks. We know this is called file, but let's just make this say everything that is a F at the beginning, or it could be an M or a T. File, mile, or tile. Any of those words would be acceptable for the match. And it returns the same 3 to us because they all start with the word file. But if we'd had a file called mile_something.txt, that would have also been found. There are other expressions that you can use besides name. You can use regular expressions. You can search based on file size or the owner, all sorts of different metadata for each of these files. But searching by name is by far the most common and the most useful. In this chapter, we're going to talk about file ownership and permissions. In Chapter 1, we learned that Unix is designed to be a multi-user environment, and ownership and permissions are important concepts in a multi-user environment. Each user on the system needs the ability to control access to their files by others. Some files may be shared, while other files stay private. Unix has these features built in. Even if you're the only user on the system, you still need to understand how they work. If you have different user accounts on your computer already, then each of these users will have a different login, and you can log in as different users to try it out. We also learned already that you can type "who am I," and it will come back and tell you the current username. Each user gets a home directory. We saw that when we opened a new window, it drops us right into our home directory. And if we type cd followed by the tilde or little squiggle, it will take us to our home directory. You can see here it took me from the My Project directory back to my home directory in users Kevin Skoglund. That value for that home directory is actually stored in a variable, and we can see it with echo, $, and then all capital home. That's the variable that Unix uses to keep track of each user's home directory. The home directory is where you're going to put most of your files. In addition to the individual user accounts on the system, Unix allows creating groups of users. Groups allow permissions to apply to a set of users. For example, if you had a group called accounting, then a file could allow access by every user that had been put into the accounting group. It allows semi-private access to a file, and group access to files is easier to manage by simply adding or removing users from that group. You don't have to manage access user by user or file by file. From the command line, you can type groups in order to see the groups that a user belongs to. Many of these groups are created automatically by the operating system and are necessary for its features to work. So you don't want to go changing them unless you know what they do. If you're an admin on the system, then you'll probably see one of the groups that's called something like admin. If you ever wondered how the graphical user interface knows whether you're an admin or not and are allowed to perform admin type things, this is one of the ways, by putting you into the admin group. Setting up and managing groups is more advanced than this course, and it's going to be most useful on servers that have dozens or even hundreds of users. It's an important concept to know about when learning about permissions, but you aren't likely to use it at first. In this movie, we'll talk about file and directory ownership. Ownership is how Unix knows which files and directories belong to you. If you own a file, you can control access to it. We can view the ownership when we type the ls-l command. The third and fourth columns in that list, the ones that say Kevin Skoglund and staff, those are the ones we want to pay attention to. The owner of these files and directories is Kevin Skoglund, and the group is staff. Now, of course, yours will be different. If we use ls space -la, that'll show the hidden files too. Notice if we scroll up a bit here that the parent directory has a different owner and group. So my user home directory, the one that belongs to me, is something I own, but the root of the system, which is a special user, we'll talk a bit more about it later on, the root user owns the directory that's above. I can't make changes to that parent directory unless the root user has allowed me to do so. Now, of course, it makes sense that files you create belong to you. If there were another user on this system, files created by that user would be owned by that user. We can set permissions based on the owner and on the group, and we can change a file's ownership. We change ownership in Unix using the chown command. That's C-H-O-W-N, I pronounce it chown. It's short for change ownership. So we use the chown command, then a space, and then we provide the username, a colon, and then the group name, and then a space, and then the path to the file or directory that we want to target. That'll change the owner and the group to match what we've specified. Let's try this. Let's go into our My Project directory, and let's do ls-la there, and we can see all the files and directories that we have, and you can see that they also have the same owner and the same group. Let's just try using the command by setting the value to the same thing that it is now. It's not going to actually change to something else. Let's just do chown, and let's do Kevin Skoglund, or whatever your username may be, and then a colon, and whatever group you already have for firstfile.txt. So I'm going to use staff, and then a space, and then the target of the thing you want to change. Now I'm not actually changing it. I have the exact same values here. So I'll hit return, and it goes ahead and executes the command. Now, if I had set it to something else, let's say I had another user on here called Bob Smith, I could type Bob Smith here, and it would change it to have Bob Smith be the owner. Now in this example, I'm just changing the values to the existing values, but it shows how the command works. I also want to show you that if you were to use chown Kevin Skoglund with nothing after it, and then the file, that would also work. It would just set the user. It wouldn't change the group. Or if we went here and we took away this, and we just put a colon followed by staff, now it will just set this to change the group. The owner would stay the same. So that's how you can change those individually. You don't have to type it all out. You can change both together, or you can change each one independently. Directories have owners too. You can see that in the list. If we told it that we wanted to change the owner of test2, then it would change just the owner of the directory, not the contents inside the directory. Whatever owner they had, they would stay the same. If we wanted it to also apply to those, we can use what's now becoming a familiar option. We can use the capital R for recursive, and that would change the ownership of this directory and all files and directories that are inside of it. All right, I'm just going to go to the end of the line and then let's erase all of that. Now let's try changing the ownership of file first to a different user. Before we just change it to myself. Let's try changing it to that root user that we saw. So change file first.txt. Let's hit return. You can see that it says operation not permitted. I don't have enough permissions to be able to give this file to the root user. In order to change the ownership, you'll probably need to be the root user or to use a command like sudo, both of which we'll talk about later in this chapter. For now, let's go ahead and just get a sneak peek at the sudo command so you'll have an idea. Hit the up arrow. I'll use Control A to go to the front of the line, and let's type sudo, S-U-D-O, in front of it. So now it's sudo chown root file first.txt. When we hit return, it's going to ask for our system password. That's the one that you would use to log into your system or maybe to make software updates. I'll type that. And now when I do ls-l, you'll see that first file now belongs to the root user. And I can use sudo to go back and change it back to be me again. Notice this time it didn't ask me for my password. It remembered that I had typed it recently. Most of the time, you're going to need to pair sudo with chown. We'll talk more about sudo in a bit. In this movie, we'll learn about file and directory permissions. Before we can learn to set permissions, we have to learn something about the notation that Unix uses to describe them. Go to your command line and type ls space -la. Take a look at that first column. The first letter, the D or the dash, indicates if it's a file or a directory, and the L tells us if it's a symlink. The next 9 characters, the ones that are R, W, X, or dash, those are the permissions on that file or directory. Let's learn what those characters mean. When you take those 9 characters that represent the file permissions, you want to look at them in sets of 3. The first set of 3 are the user permissions. The second set are group permissions, and the third set are permissions for other, or everyone else in the world. User, group, and other are the 3 categories of permissions. Each category has 3 permissions to it. We can set read permissions, whether or not you can read the contents of a file or directory, write permissions, whether or not we can actually make changes to a file or to a directory, and then execute. For a file, that means that we can run it like a program or script. For a directory, it means that we can search inside of it. This table has the 3 categories at the top: user, group, and other. And the 3 types of permissions are on the left: read, write, and execute. A permission is either enabled or disabled. So in the table, if it's enabled, I put a single letter abbreviation in the grid, either R, W, or X, for read, write, and execute. If it's disabled, I put a dash or hyphen to indicate that it's turned off. When we put those together, we get a 9-character string. Here, the user can read, write, and execute. The group can read or write, and everyone else can only read. Now we can read the list of permissions. For example, file_first.txt has permissions rw-r-r-. That means that the user, or the owner of the file, in this case myself, can read or write the file, but cannot execute it or run it like a program. The group, which we can see as staff, can read the file, but can't write to it or execute it. And everyone else in the world can also read it, but can't write it or execute it. You can see a little further down that the lorem ipsum file has some slightly different permissions. In that case, the group, staff, can also write to it, and so can anyone else. This RWX alpha notation is not the only shorthand for permissions. Unix also allows something called octal notation. Imagine that every time you have an R, it's equal to the number 4. And every time you have a W, it's equal to the number 2. And every X is equal to the number 1. We can use these then to perform some math. Let's take the same table that we just had before, but replace the R, W, and X with those numbers, and the dash will be equal to 0, of course. When we add them together, going down each column, you can see we get the numbers 7, 6, and 4. So those same permissions that we wrote out with 9 characters, we can now write with simply 3 characters. It's much more efficient. Now, this may seem daunting to you at first because there's a lot of concepts that are going on here. But once you start using it, it gets pretty easy quick. And the reason why is that there's only really 4 octal numbers that you use: 4, 5, 6, and 7. 4 would be if you can read the file only. 6 is if you can read and write. And 5 is read and execute. And 7 is all 3, read, write, and execute. So once you get the hang of those 4 values, it becomes very easy to set a file to 755 or to 644 and to know what those mean. In the next movie, we'll take what we've learned about this notation and learn to set permissions. Now that we understand alpha and octal notation for permissions, we're ready to set them in Unix. Remember, alpha notation uses R, W, and X as a series of 9 characters to say whether something has read, write, or execute permission for the user, group, and other categories. The way that we would change those permissions is using the chmod command. That's CHMOD, and it's short for change mode. So I guess you could also pronounce it as chmod if you prefer, but I call it chmod. You'll see that right after the command, I have notation for the groups that I want to set. In this case, I've got U, G, and O, and I'm setting it equal to R, W, and X. And then I've got the path to the target file or directory. So in this case, I'm setting user, group, and other all to have read, write, and execute permissions. Now I don't have to set them all to the same thing. I can also put commas between the list. So here I'm setting user equal to read, write, and execute. I'm giving group read and write permissions, and everyone else gets read permissions only. You can also use plus or minus to add or subtract permissions. So in the next example, I'm telling it that I want to add the write permission to the user and group settings. In the last example, I'm telling it that I want to take away the write permission from the other settings. That's how you use alpha notation. We also talked about octal notation, where we use the numbers 4, 2, and 1 to represent those values, and then add them together to get a series of 3 numbers. We can use chmod with those values instead. You can see it's much more efficient. We can just say, I want to set it to 777. That gives all permissions to all categories. Or 764. That would be all permissions for the user. It would be read and write permissions for the group, and it would be read-only privileges for other. And you can set 755 or 400. From the command line, you can see that I'm still in the My Project directory. We can get an idea of what files and directories are in there. Let's try chmod and then ugo equals, and let's set it to R and W for file underscore first.txt. And now when I type ls-l, you can see that the permissions are R and W for all of the different categories: user, group, and other. And that's different than what we had before. Let's try another one. Let's set chmod. We'll set user equal to rwx, and then let's set group equal to rx, and other equal to rx. We'll do it again to the same one, file first, ls-l, and now you can see it's set it to rwx, r-x, r-x. Let's try adding just one setting. We'll do that with the plus. So to the group, we'll add the write permission. ls-l will show that the permission has now been added. And let's try taking away permission. Let's say chmod, and we'll say that the other ought to lose its read and execute permissions on file first.txt. ls-l, and we can see that now those permissions are gone. That's how we use alpha notation. Let me just clear my screen, and let's try it again with 777 for octal notation with file first.txt. And now we can see that it added all of them, read, write, and execute, for all 3 categories. Let's try, I'll hit the up arrow, save myself some typing. Let's go back here and just change this to be 654. And you can see that the permissions changed. And last of all, let's go up and change them to 744. And look one last time. You can see now it's given read, write, and execute permissions to the owner. Everyone else has read permissions. We can do the same thing with directories, chmod and 744 on test 1. Now, if I do this like this, it'll change the permissions for the directory only. Just like we saw before with chown and copy and some other things, we can use the capital R option to make it recursive. This says take the directory test1 and all files and directories that are in it and set all of their permissions to the same thing. So now that directory and everything in it will have that same permission. When you're a single user in Unix, you may not run into permission issues that often. But the one place that it does sometimes come up is if someone else gives you files and you bring those files onto your computer and you don't have the ability to access them. Changing the owner or the permissions or both may allow you to access files that Unix won't let you access otherwise. In this movie, we're going to learn about root, sudo, and sudoers. The root user is the most privileged user account. It can do absolutely anything on the Unix system. It can open any file, it can run any program, it can change any permissions. It's an all-powerful user that's not bound by normal user permissions. In fact, it can create new users and delete the accounts of existing users. Have you ever watched a movie or TV show where there's some hackers who talk about getting root access or being root? This is what it refers to. If a hacker can get root on a system, they can access and change anything that they like. But logging in as the root user is not the only way to get that level of access. The sudo command grants the privileges of the root user. Sudo stands for substitute user and do. It's not super user do, as some people guess. Most often, it's used to perform an action as if you were the root user. Sudo is used as a prefix to other commands. So for example, we have the command cat file.txt, which would try and show us the contents of a file. We can put sudo in front of it to run that command as the root user. So we can substitute the root user and say, this request is not from me, from my username. This is a request coming from the root user. It's asking you to show this file. So maybe I don't have permission to see this file, but the root user does. It can bypass the permissions that have been set. We saw how this was necessary earlier when we were changing the file ownership using chown. In your command line, type sudo, and then let's use a command, and the command we're going to use is who am I? We know what who am I normally returns. It returns our username. Instead, when I run sudo, it's going to ask me to give my password. It wants to make sure that I have permission to do this command. So that's going to be my regular user password, not for the root user, but for my own account. And then it does run the command. Notice that it came back and said that the user is root. So it substituted the user root, and then that root user ran the who am I command. If for some reason this didn't work for you, then hang on a second and I'll explain why. If we hit the up arrow and we run the command again, you'll notice that this time it doesn't ask me for my password. That's because the password authentication stays valid for a little while, for about 5 minutes. It's configurable on different systems. You can use sudo with the -k option if you want it to expire right away. You can also use sudo with the -u option if you want to specify a different username on the system. Maybe you've wandered over to someone else's terminal, you want to show them a file you're working on, you realize that they don't have permission to do it, you can then substitute your own user and be able to show them the file. Not everyone can use the sudo command. If you're an admin of the system that you're working on, then you should be allowed to use it. The reason why is because in Unix, there's something called a sudoers file. It's located at /etc/sudoers. And if you notice when I run it, it says that the permission's denied. That's because we shouldn't be able to see who's in that file unless we have permission to do it. Now I am a sudoer on my machine because I'm an admin, so I can run that same command, and this time it will give it to me. There's the contents of the file. Notice these last lines right here. These are the important ones that you want to look at. The users and groups that are listed here are the users and groups that have the ability to use sudo. They are the sudoers. So you can see that the root user has permission to do everything. That's what that all equals all means. We won't worry about the different options that you could put there. This is essentially giving permission for the root user to do everything. And it also says that anyone in the group admin can also do everything. When you set a user as an admin in the graphical user interface for the operating system, it adds that user to the Unix admin group, and the user can then run commands as root. Or you could just edit this file to add users or groups to this list. Before we move on, I want to show you a super useful shortcut in Unix. It is sudo space exclamation point exclamation point. What this says is do the last command, but this time using sudo. It's super helpful. Let's say that you try to view a file and it tells you permission denied. Well, you can use sudo space exclamation point, and it will then run it. For example, I previously took a look at the sudoers file without using sudo, and it said I couldn't do it. But if I do sudo space and then 2 exclamation points, now it runs the same command, but prefixing it with sudo. I find it's very useful. In this chapter, we will discuss Unix commands and processes. Unix commands are just small programs, and those programs are really just files in the file system that have code in them. And of course, we need to be able to run them, so we want to have permission to execute that code. And that's it. It's a file that has code that we execute. Many of those files are stored in either the bin directory or in the USR bin directory. If you go to the command line and you type which followed by the name of a command, like cat, it'll tell you the location of the cat command that you're using. /bin/cat in this case. That means that the file name is cat and it's in the bin directory. We can do which ls for the ls command and see it's in the same place. If we do which banner, we learned the banner command earlier, we can see that it's stored in a different place. It's in the USR bin directory. Each one of these is a small little program that we execute. For almost every Unix command, there's also an associated manual page or information about how to use that command. We call them man pages for short because the command to get to them is man space and then the name of the command. So I'm asking for the manual page for cat, and it will open up documentation on how to use the cat command. This is using the more pagination tool that we saw earlier, so we can hit the space bar to go forward or F or B to go forward and backwards pages. We can use the up and down arrows. And the man pages tell you how to use the command, as well as give you information about all the options that you can use with it. So for example, we see here that the cat command can use the in option in order to number the output lines. The manual pages are super useful and a really good way for you to learn more about how the different commands work and what different options are available for them. So how does Unix know how to find these commands? After all, the ls command was stored in this directory, while the banner command was stored in a different directory. How does it keep those straight? It does that using a variable called path. And we can see that value if we use echo space $, and then in all capitals, PATH. This is my current path value. Yours may be different than mine. As we'll see in a moment, it's something that we can customize. This string is a list of the directories where Unix will go looking for commands, and in the order that it will go look for them. So the very first place it'll go look for the command is in that USR local bin directory. Then it will try USR bin, then just bin, then USR sbin, and then sbin. So if the command happens to exist in more than one place, it gives them an order of preference as well. We can demonstrate how this works by changing the path variable. Let's use capital PATH equals, and then let's use the same part of the name, but let's leave out the bin portion here, everything from bin forward, because that's where the ls command is. So you can just copy and paste all of this, or retype it, and then hit return. Now, if we hit the up arrow and echo the path value again, you'll see that it's been changed. So now let's type the ls command to list the contents of the current directory. It comes up and says, sorry, the command's not found. It looked in those two places that are in my path, and it didn't find it in either one of those, so it gave up. We can go ahead and change this value back just by adding in the rest of this. I'll just copy it, or you can retype it, and then hit return. And now when I type the ls command, you can see it works again, because now it looked in this directory and found the command there. The path is an important concept. A lot of the built-in commands are going to be found because they exist in these regular directories. But if you had your own custom commands, or if you installed other software, like a database program, it might have commands that sit in a different directory, and you'll have to amend your path so that it also looks in those directories to find those commands. One final thing I want to note is that when you set the path variable in this way, inside the shell, it's only keeping that path for this current session inside the shell. If we open up a new window, or if we close this window and open a new one, it would revert back to the default path again. In a later movie, we'll learn about configuring your environment, and we'll learn to make that change permanent. In this movie, we're going to learn about some commands that provide some useful information about the system that we're working on. We're going to be looking at several. We're going to learn about date, uptime, users, who, uname, df, and du. Let's go to the command line and see how they're used. Let's start with the date command. It does exactly what you'd expect. It returns the current system date, whatever the system date has been set to. We can also use uptime, and it will tell us how long the system has been online. You can see that it's been 1 day and 31 minutes since my computer was rebooted. Sleeping the computer doesn't count. This is only from reboots. It also provides some other information like the current time, the number of users, and the load averages. A better way to find out what the users are is to type users, and it'll give you a list of all users who are logged into the system. Right now, I'm the only user logged in, but I'm actually logged in more than once. If we type the who command, we saw earlier, this tells us about all users that are logged in and gives us a listing for each one of those logins. So if I open a new window now, so that now I have a second login, and I type who, you'll see that there's a third one that appears. So this first one is the window that I'm in now. This one is the window that's over here. I'll close that up. The one that's here at the top, the one that says console, that is the login that's outside this window. That's the actual desktop environment, and it got logged into Unix when I first booted up the computer. So even if I were to close this window, the outside desktop environment would still be logged into Unix. We can find out more information about the system that we're logged into with the uname command. By itself, it just returns the name of the flavor of Unix that we're using. I'm using a Mac OS, and Darwin is the name that Apple gives to their version of Unix. If I use it with the -a option, though, I get a lot more information. It tells me not just the Unix name, but also the machine hardware name, the node name, the OS release, the OS name, and the OS version. If we run it with the -p option, it tells us the processor name. One question that often comes up when working with the system is, how much disk space do I have free? And how much disk space does something that I'm working on use? We have a couple commands that can help us with that too. I'll use clear first, and then let's use df, which is short for disk free space. So it tells us the amount of free space on the disk. Let me just expand this window a little bit so you can see all the output there. Here you go. This is telling us how much of the space is used and how much of the space is available. Unix thinks of disks in terms of different volumes, so it's showing you the disk space on each one of those volumes that it sees. Now, this number is a little hard to read, so when I use df, I usually pair it with the -h option, lowercase h, and that will give me a nice human-readable version. So I can see here the size of the disk, how much of it has been used, and how much of it is available. If we want to know how much space something takes up on our hard drive, whether it be a file or a directory, we can use du, which is for disk usage. It'll tell us the size of it. It's a little bit like getting the info on a file in the graphical user interface. So du, and then the path to the file. You always want to use a path. You don't want it to give you disk usage for your entire hard drive. So give it a path. I'm going to say look at the My Project directory, and that's what we want it to tell us the disk usage for. I'll hit return, and it comes up and it gives us a list of not just the My Project directory, but every directory that's inside of it. If we use du with the -h option, then it gives us those in human readable format. I'll do that again. You can see now it has those in terms of kilobytes. Now this is the blocks of space used. It's not the actual size, so it usually rounds up a little bit. That's why it says 4K. That's the smallest size. There's not actually 4K of information that's in those directories. We can also add the A option if we want it to report back all of the files that are in there as well as the directories. You can see now it gives me the size for individual files. And it's very useful sometimes to use the D option. Let me hit the up arrow. I'll take away the A option, but I'll leave the H option. Let's do -D and then a 1. I'm telling it that I want it to calculate it to a depth of 1. And we'll see the difference here. Let's do it first of all with a depth of 3, and then let's just change it to a depth of 1 so we can see the difference. Notice what is different between these is this entry right here. It did not descend into the test2 directory. It only did my project and one level deeper. If we make it a depth of 0, then it tells us just the size of that directory, which is very useful. It says, go and tell me just a summary for this one directory. What is its total size? Together, these make up some useful tools for finding out information about the Unix system that you're working on. In Unix, whenever we run a command, it launches a program, and that program contacts the kernel of the operating system and asks it to allocate memory and resources for it to be able to run its code. We call that a process. And the process may be very short-lived and give the user a really quick response like ls does, or it might be something that takes a long time. There can be processes that continue running throughout the time that you're using the system, and there may be background processes as well. In this movie, we're going to learn how to view and monitor the processes that are running. We're going to do that using two commands, the ps command and top. PS is short for process status. Let's look at it first. If you go to the command line and you type PS, it'll return a list of the processes that are your processes, the ones that are running that belong to you as the logged in user. You can see that I have only one process running, and it's the Z shell that I'm currently working in. More useful is to use PS with the -A option, and that'll give us a list of the running processes that are owned by all users. You can see that there are other processes that are related to me, but they're not necessarily owned by me. Chances are they're owned by root, even if it's something that I started. For example, one of the processes is the command that I just issued, ps space -A. At the time that it reported back, that was a running process. We can also use PS with the -X option to look at all of the processes. It's going to be a very long list. We can combine it together with the A option, but I also want to show you that it works if we take away the dash in front of it. And the reason why is that PS has an old style version and a new style version. And one of the main differences between them is how it uses the U option. PS AUX works and will return back a list of the processes, and it tells us who owns each of those processes. So you can see here, it tells me now my username. However, in the newer version of PS, you can't add back in the dash because the U option has changed. The U option instead now is used to find processes that belong to a particular user. In this case, here's all the ones that belong to root. I don't find that nearly as useful. Let's clear the screen and let's run ps aux like that. So we'll type ps aux and then let's scroll the top so we can see all the information that it's giving us. You can see that I have user as the first column. PID is the process ID. Every process is given an ID number. We can see the percentage of the CPU that it's currently using, the percentage of the memory. This is about the virtual memory and the resident memory. We have the time that it started, the amount of processor time that it's used, and the name of the command, which tells us the path to the file that's actually running. So if you have a process that's not behaving correctly, you can scan through this list and see if you can find out what's going on. Another useful tool is top. If we just type TOP, it'll clear the screen for us and it'll give us a running dashboard of the different processes. So this is updated every couple of seconds. It's configurable how many seconds we use for refreshing. You can see that it tells us information at the top about the CPU usage, about the amount of memory that it's taking up, and then it gives us those columns where it shows us the process ID, the command, the amount of CPU it's using, and all sorts of other information, the memory, and so on. The version of top is a little different on different versions of Unix, so yours may not look exactly the same as mine, but the principle is still the same. It'll keep running until we type Q to exit out of it. Before we do that though, let's type a question mark, and you should get a help screen. This will tell you information about the various options that are available to you. So for example, you can change the order in which it sorts, or the delay time, or filter it by particular users. Again, these options and the way that you use them vary a little bit depending on your version of Unix. I'll hit a space key to exit back out of there, and then Q to get out of top. Together, these two commands, ps and top, provide useful information about what's happening on the Unix system, what processes are running, how much CPU space they're taking, how much memory they're taking, and that can provide important insight into what's going on. Now that we understand about Unix processes, I want us to talk about how you can stop processes. There are a number of different ways that we can stop processes in Unix. The first and simplest is just to let the process finish. It may take a minute or two, but it's the most graceful thing, just to let it do its job. If we're inside a program where we have some communication with it, like a nano text editor, for example, or the man pages, there may be a way to gracefully exit out. And we can usually do that with either Q, Control Q, colon Q, X, Control plus X, or the escape key. The more common ones are towards the front of the list. And it usually depends on the program that's actually running. So the programmer of that program gets to make the choice about whether you use Q or colon Q in order to quit out. If you can't gracefully exit out of the program and you need to do so forcibly, you can do that using Control C. Control C is kind of the universal way in Unix to tell a process that it should stop. So you've got something that's taken control of your window, it's a running process that you're in the middle of, and you want to stop it. This would be useful, for example, if I used cat on a document that was 10,000 pages long. As those pages start scrolling by, I realize my mistake. I can hit Control C to tell cat that it should stop. Another option that many are tempted to use is closing a window. And that may do the job, but the process may keep running. So in the example of a long document that you're outputting, that document still is probably being output, you're just not seeing it on your screen. And if you open up a new login window, you'd be logged in and able to continue working while it finished going through the rest of that document. Sometimes that just gets the job done, but it's not ideal. Usually what we'd really like to do is to kill that process off. And especially if the process is running in the background, that may be the only option we have. We can't gracefully control it because it's in the background, and we can't force quit out of it because it's not in our terminal window right now. So we need to know how to kill off processes. In the previous movie, we learned to use top, and it'll show us the running processes and give us an updated list. You'll notice that it has the PID for each one of those. That's the process ID, and that's going to be important for us to know. Let's imagine that we have a process that's gone out of control, and it has 99% CPU usage, and it's just made my whole computer come to a stop. I need to kill it off. It's not going away on its own. I need to kill it off. Maybe it's stuck in some kind of a loop or something. So I'll hit Q to gracefully exit out of top, and then I can use the kill command in order to kill off the process. Kill followed by the process ID number. Now I don't have one of those processes now, so I'm going to just imitate it. Let's use PS, take a look at the processes that are there, and then I'm going to open a new terminal window. Here we go. If we come back over here and we type PS, you'll see that now there's a new entry. This was my old one, 2310, and here's the new one, 2650. So this is now my process that's going to be my bad process that I want to get rid of. How can we kill it off? Well, we know its process ID number, so we use kill space 2650. Did that kill it off? We click back over here. Nope, it looks like it's still running. We're still able to look at the commands. If we type PS, you'll see that it's still there. Now, kill sometimes will kill off a process just like that, but more often than not, you're going to need to use kill with the -9 option. It's so common that I just go straight for it. When I want to kill a process off, I use kill space -9 and then the process ID. Now this time when we run it, the process will be killed off. You can see that it's gone now. And then when I come over here, it tells me process completed. We can close that window because we can't use it anymore. Now don't go crazy with this kill command. Kill off only processes which are really causing you a problem. You don't want to start killing off processes that the operating system might have launched when you first logged into your computer and that it might still be expecting to have running. In this movie, we'll learn to use Unix's command history. Unix keeps track of the commands we use, and that history is a useful reference that can help us to work efficiently. The way you can view the command history is with the history command. Type history and hit return, and it will return a list of past commands in the order that you use them. Your list may be different than mine. You may have entered different commands, and your version of history may be configured differently. We'll talk more about that in a moment. These are the same commands that we can access by using the up arrow. History just gives us a list of them. You will also notice that the history accumulates over time. If you type some commands and then log out and come back the next day, the history will still include those previous commands. Unix remembers the history by storing those commands in a file. And we can see that file if we're in our user home directory, ls-la. Make sure you use the -a option so we can see the dot files. Here's the history that I have for the Z shell. It's called .zsh_history. If you're using bash, it might be called bash history, or if you're using one of the other shells, it might be called sh history or something different. The idea is the same though. It stores these commands in the file so that it can remember them. Whichever one you use cat to take a look at it. .zsh_history for me, and you'll see that it's just a list of commands, one per line. When we log out, Unix saves our current history to this file. When we log back in, Unix reads this file to restore the history to its memory. That's also why this list is not as up to date as what the history command shows. If I type history, you'll see that I have some additional commands here that are not listed in that file. It only saves it at logout. That history file is really for Unix's use, whereas the history command is meant for your use. Another difference between the two lists is the addition of those reference numbers in front of each command. We can use those numbers to refer to the commands. Let's look at how two of the popular Unix shells allow us to use options and reference numbers with the history. It's important to talk about because the bash shell, which is very popular, and the Z shell, which is becoming more popular, both work with history in different ways. If we just type the history command in the bash shell, you get back all of the history entries. Some of you may have experienced that. Whereas when I was working in the Z shell, I only got back the 15 most recent ones. If you provide a number after history, the bash shell will give you that many of the most recent entries, whereas the Z shell will look at those reference numbers and give you entries starting with that number. Similarly, if we did history with just the 1 after it, bash would just give you the 1 most recent entry, whereas Z shell would give you all of the entries, starting from the very beginning. We can also use a negative number when we're working with the Z shell to get the most recent entries, similar behavior as we get without the negative number in bash, but in bash that doesn't work at all. I'm in the Z shell here, so you can see when I typed history, I just got the 15 most recent commands. If I instead type history, and then let's type 25, just go back another 5, you'll see that it gives me a slightly larger list going back to 325. If I type history 1, then it'll give me my full list. You can scroll up and see it goes all the way back to the very beginning. History -5 will just show me the 5 most recent commands. Let's contrast that with bash. I'll log into bash just by typing bash, ignore that message that it gives me. I'm going to clear my screen, and let's just type history here, and you'll see that I get that full list of all the commands. If I type history 15, it gives me back the 15 most recent commands. Remember, the Z shell gave me everything from 15 if I did that. And then let's try history 1. That just gives me the most recent command instead of going back to the beginning. History -5 doesn't even work. So that's in the bash shell. I'll exit out of the bash shell, so I'm back in the Z shell again. And it's something to remember if you're switching between shells. In this movie, we'll learn to use some handy shortcuts to run commands that are in the Unix command history. There are some other useful shortcuts that make use of the history. Let me clear my screen again. They all start with the exclamation point. So let's just do history so I can see just the last few. If you're on bash, you might want to do something like history 15. Now let's pick one of these commands that we want to run. Let's just run 340 because that's nice and simple. It's just going to show me the current working directory. So if I were to type in 340 with no space after it, it'll execute that command. It tells me what command it's running, and then it does it. That's very handy. We can look back through the history, pick the command that we want, find its reference number, and just put an exclamation point in front of it to execute that command again. Be careful though, if your command includes a relative path. For example, here, I'm looking at the contents of a file that's in my current working directory. So of course that command is only going to work if the directory that I'm currently in has that file. We can also use the exclamation point with a negative number to execute a command that occurred a certain amount of time ago. So this is -5, for example, 5 commands ago. I'll run that and you'll see that it did a history command. If we scroll to the top, you'll see that it is a long history command, but here it is. It's history1 is the command that it ran. That was the command that was 5 commands ago. Let's type history. You can see that it's now a little further back. That can be a little tricky to figure out how many commands ago something was. It's most useful, I think, when you use -2 as a try again measure, right? You try something, it doesn't work, you do a different command, and then you can do it with exclamation point -2 to try the previous command again. We already saw that you can use the exclamation point to run the same command again. So for example, let's do pwd, and then let's do exclamation point, and it does it again. That was useful when we were looking at chown earlier. Let's go into our My Project directory for a moment. And in there, I have a file called file_first. I'm going to do chown root file_first.txt. It didn't work, but now I could do sudo exclamation point, and it refers to that previous file, and it will make the change. I'm not going to do it because I don't want to have to change it back. So I'm going to leave it for now. Another very useful one is to use the exclamation point followed by a keyword. So if we wanted to run a command that was in the past, let's say we wanted to go back to the last time that we ran the cat command or the nano command, or maybe we were running MySQL or something like that, we can just type the characters of the command here and it will pull up the last instance of it. For example, we use du for disk usage. I don't remember what options we gave it, but let's try it again. Exclamation point du, you can see it pulls it up. Here's the previous command, and then it ran it. That's a nice shortcut. Another good one is that you can use the exclamation point with the $sign to refer to the previous argument. Let me just clear my screen. I'll do nano.file_first.txt. Let's say I make some edits to this file. I do Control X and exit out of it. And now I wonder if I made the change that I meant to. I want to take a peek at it. I can do that with cat exclamation point $sign. This is going to use the cat command with the argument to the previous command, file_first.txt. And you can see that it outputs that. So just so you can see all these shortcuts in one place, I'll put them here. We have exclamation point with the number, exclamation point with part of a previous command name, double exclamation point, and exclamation point with a $sign. I think you'll find that using the command history can allow you to work much more efficiently. In this chapter, we will learn to direct input to Unix commands and to handle the output that comes out of them. Unix has standard inputs and outputs. Standard input, sometimes abbreviated as stdin, is going to be the keyboard by default. And that makes sense. When you're interacting with Unix, typically the input is coming from the user, from the keyboard. We also have a standard output, or stdout for short. And by default, that's typically the text terminal, or the screen. Again, that makes sense. We enter a command, the command gives us output back to the screen. But those aren't our only options. Let's begin by learning how to send output to a file instead of to the text terminal. We do that using the greater than operator. So you have a Unix command, it can be any Unix command that you want, but after it you're going to have that greater than operator that points to a file. And it even looks like a pointer. It looks like it's sending data from the command to the file. And on the right side of that greater than sign, we're going to have a path to a file. And that's probably a file that doesn't exist yet. In most cases, we're wanting to take the command and store data in a new file. From the command line, you can see that I'm already inside the My Project directory, and I'm just going to first start by doing echo and then hello. You can see I gave it input from the keyboard, and the output was back to the terminal. If instead I want to send that output to a file, then I just take the same command, and I use that greater than sign followed by the file name where I want to save it. This could be a path anywhere, but I'm going to put in my current working directory. I'm going to call it banner.txt. I'll hit return, and the first thing you'll notice is I did not get any output this time. Before, the output came here to the screen, but this time it didn't. It was sent to that file. We can do cat banner.txt, and we can see that's where the output is. It's the exact same output, it's just got sent to the file instead of to the screen. We can use this same technique with any Unix command. Let's try another example using banner. We saw that banner-w50 and Unix rocks will just output a long banner to the screen. And scroll up and you can see it has banner turned sideways. There's rocks. We can take that same thing and we can send that to banner.txt. Now notice it didn't give me output this time, but if I take a look at banner now, you can see it contains that same information. If you scroll up to the top, you'll notice that it replaced the data that was already there. That's a very important point. When we direct output, it is destructive. It overwrites anything that was in the file before. I want to give you another example. Let's do ls-l, and you'll notice that I have two files here, file first.txt and file second.txt. We know that we can use cat to concatenate files together. It's not just for viewing files, it actually is meant to concatenate them together. So if I just have a couple of file names in a row, it'll output those files one after another. What's most useful though is if I do that with that operator, I can then send those to a new file. Let's call it file joined.txt. I get no output here, but if I take a look at file joined, now I have the contents of both of those files concatenated together. It's a very handy way to join files in Unix. If we don't want the output to completely replace the contents of the file, we can instead append the output to the end of the file. And it's very easy to do. We just add another greater than sign after it. So one greater than sign replaces the data, two greater than signs appends the output to the end of the file. Let's create a new file where we can see this. I'll use nano and I'll create a file called people.txt. And I'm just going to put some people's names in it. Linda, Bob, and Susan, and Larry, and Anne. Okay, now at the very end, let's make sure that there's only one line return after Anne. If I hit the down arrow, you can see I actually have two line returns because it gave me one there by default. So delete one of those. You should not be able to hit the down arrow again after that. So it's Anne with a line return and nothing else. That's going to be important when we append onto this. I'll do Control X to exit and save my changes. And now let's try appending onto this list. Let's add on Claire. We'll use that append operator and then the name of the file, people.txt. You can do the same thing with John, people.txt. And now when we take a look at people.txt, it did not replace the data, it added those two names to the end of the list. Redirecting the output from a Unix command into a file is a powerful and useful technique. In this movie, we'll learn how to use a file as input to a command. It's much less common to direct input to a command than to direct the output from it. It's not because file input is uncommon, it's because it's so common that most commands take a file as an argument. But for commands that don't, we can direct input to them anyways. And we can do that by using the less than operator. Exactly the same as we saw with output, but pointing in the other direction. So I have the command, and then the less than operator, and then the file that I want to send as input. Of course, this has to be a file that actually already exists if I'm going to use it as input. It may seem odd at first to have the input come after the command, but Unix wants it this way. Unix wants the command to be the first thing on the line, and then the input operator is that less than sign. If it was on the other side, it would be using the output operator, which tells Unix to do something completely different. Let's start with a really simple example. Let's say that we just cat that file first that we have. In this case, I'm using the cat command, and the argument to it is file_first.txt. You can see it's so common that we want files as input that it takes it as an argument. But we also could do cat and then the less than sign followed by file first.txt. This is going to say take the file and use it as input to the cat command. The difference between these is subtle and the output is the same. Let's try another example using a command that we haven't seen yet called sort. With sort, we can use the input from people.txt, which is a list of people's first names, and it will sort them into order for us alphabetically. Now you may be wondering, well, what if we want to take that list and we wanted to save it as output? Well, we know how to do that. We would sort the people list and then take the output and send it to sorted_people.txt. I don't get any output here, but inside sortedpeople.txt, I now have my list. If you're going to use both, you want to use them in this order. You want to have the input first and the output second. If you flip them around, Unix wouldn't be able to understand what you meant. Now, sort also uses a file as an argument because it's so common, so more often you would see something like this instead. Sort people.txt passed to sortedpeople.txt. Either one works. You may be wondering what the point of this is if so many Unix commands take a file as an argument. Well, there are some commands that don't. Let me give you two common examples. If you wanted to send email using Unix's built-in mail program, you could do that by using mail with a couple of arguments, and then if you had the message that you wanted to send in the email stored as a file, you could then use that file as input to the command. Or if you were working with MySQL and you wanted to run a series of MySQL statements, perhaps it's a database backup file, you can take that file and use that file as input to MySQL, and it'll execute those commands for you. You'll find yourself directing output more often than input, but it's important to know how to do both. We've seen how to send data from one command to a file and from a file to a command. In this movie, we'll learn to send data from one Unix command to another Unix command, and we'll do that using a technique called piping. The way that we pipe output to input is by using what we call the pipe operator. And it looks like a pipe. It's that vertical bar. You probably will find it on the far right side of your keyboard above return. Unlike the previous examples, there's no file involved here. We have one command that's on the left, and its output is going to become the input to the second command on the right. To demonstrate this, let's start by just taking a look at what's inside the people.txt file. I'm using the cat command in order to do that. In this case, the output from the command went to the terminal window. If we instead use that pipe operator, we can send that data somewhere else. Let's send it to the sort command. So I have two commands, cat and sort. The output from cat becomes the input to sort. And you can see it gives us back a sorted list. Now the output from sort still came out and went to the standard out, which is the terminal window. But the output from cat did not. The output from cat went straight into the sort command. Let's try adding another name to the list. Pick one of the names that's in the list. I'm going to use Larry. And let's append that on. We learned how to use the append operator already. So now we have two Larrys in the list. Now let's hit the up arrow and let's run that command again. And you'll see that we get that duplication in there. Let's now hit the up arrow again and let's pipe the output from sort into another Unix command called unique, UNIQ. No UE at the end, just UNIQ. We'll hit return and you'll see that it deduped that line for us. So now there's only one Larry in the list. So we took the cat command and took its output and sent it to the sort command. Then the output from the sort command was sent to the unique command, and the unique command then sent its output back to the standard out. Let me show you a couple of other places where this comes up. Let's say that we have something that generates a long list, like PSAUX that we saw earlier. It's showing the process status. Right? This is a very long list, and I would have to scroll to the top to see what's there. I could also take PSAUX and pipe it into less. We know that less is the pagination tool. Now I get a paginated list of that information, and I can hit space, I can hit the up and down arrows to move through it, and Q when I'm done. Or I could use PSAUX and pipe it through another command we haven't learned yet called grep. Grep is a regular expression search tool. It's more advanced than what we're going to talk about in this course, but if you provide a keyword after it, like login, it'll essentially search for any line that contains login. So I'm piping the PSAUX through grep, and grep will filter it and only show me lines that match. We'll hit return, and you'll see we get back just a few lines here. Make this a little wider. You can see that it's got 4 different lines that have something in them that matches login. That's a very handy way to search the process list. Piping output to grep can also be useful when working with your history. I'm using the Z shell editor, so when I type history, I just get back 15 of my most recent commands. If you're using bash, you probably get all of them, a very long list. I can get the same thing in Z shell by using history with 1. It'll go back and show me all of the things in my history, but I don't want to see that full list of 652 items. Instead, let's pipe that information to grep, and let's ask for nano. Any line in my history that has nano in it is going to show up. Now, instead of having to comb through a long list, I can find exactly what I'm looking for. The important thing to remember when piping is that it's always from one Unix command to another Unix command. We know how to send output to the screen and how to send it to a file. But what if we don't want any output at all? In this movie, we're going to learn how to suppress output completely. To do that, we need to know about something in Unix called dev null. Dev null is often called the null device, or the bit bucket, or the black hole, and it works a lot like a file. We can direct output to it, and any data that goes there will be discarded by Unix. So it's like sending data to a black hole. It just disappears. Once you know it's there, using it is very easy. For example, let's do ls-l, and of course we get a listing of our current files, but if we instead take that and send the output to /dev/null, then we get no output. It didn't send it to our screen, it didn't send it to a file, it just went nowhere. All output was immediately flushed by the system. Let's try another example. Let's cat the lorem ipsum file, and let's put that in dev null. All that output from that command was simply flushed away. As a beginner, you may be wondering why you might have a reason to use this. Well, it's most useful when you're running jobs that perform an action and then also return output. So you still want them to perform the action, you just don't want the output. We may want to skip that output. For example, if we're running a command from a timed script that's going to run at 4 a.m. every morning, we might want it to perform the action, but not give us any output because we're not around at 4 a.m. For example, maybe we're running a script that backs up the database, and we want it to perform the backup of the database, but any results, errors, or warnings that might be generated, we don't want to keep those, we want it to just flush them away. Once you understand both the concepts of how to direct output and the null device, then it becomes easy to suppress any output. In this chapter, we'll learn how to configure your Unix environment. To configure your environment, you're going to add code to one of several files, and the files that you'll use depend on the Unix shell that you're using. But the different files have a lot of similarities. So let's start by looking at the very popular bash shell to get an idea. When you first log into a new bash shell, Unix is going to process a couple of different configuration files. They're both dot files that exist in the base of your user home directory. That's what that little tilde at the beginning indicates. So we have bash_profile and bash_login. Bash profile is the main one. Login is really there mostly for legacy purposes and doesn't get used very often. There's another configuration file called .bashrc with no underscore that also can exist in the user home directory. This is the file that gets run whenever bash starts up a new subshell. In other words, not a login shell. So if I go into a bash shell and I log in and then I type the word bash, I will now be opening a new bash shell. In that case, bashrc would run. And then the fourth file that you need to know about is that when you log out of a bash shell, it'll run any commands that are in bash_logout. In truth, you won't use that very often. You're much more interested in setting up your environment when you first log in or when you first open a new shell. So where should you put your configurations? As a beginner, you can put everything in bash_profile. That's the simplest explanation that I can give you. Put your configurations in bash profile. However, that's not perfect because if you open a new bash subshell, those configurations would not get applied. So you would have to duplicate them in bashrc also. Now, as a beginner, you're not going to do that very often. You're probably going to be just working in one shell, but it is good to know about that difference. If you want, you can put in bash profile a bit of code that'll tell the bash profile to always load what's in the bashrc file. Then you can put most of your code in the bashrc file and know the bash profile will load it as well. We're not going to talk about what this code means, but you can type it into your bash profile if you want it to work for both. I'm going to be working in the Z shell, so let me give you an example that shows the differences between bash and the Z shell. When I log into a Z shell, I'm going to have similar files, but there are some differences. It's going to load the zshenv file, an environment file, then the profile, then the RC, and then login. So you'll see that it's a little bit different from bash in that zshrc shows up in that list. When you start a new Z subshell, it's going to also run that zshenv and the zshrc file. Because those two files show up in both lists, it's already set up and ready for us to use either one of them to put our configurations. As a beginner, I recommend you use zshrc for everything. If you're using a different shell, you can look at the reference information for that shell, or you can go on Wikipedia where they list some of the most popular shells and give information about the files and load orders that are used. From the command line, we can see this. If we go back to our user directory, cd and then the tilde to let us go back to the user directory, ls-la, it's important to have that a there so we see the dot files as well. And here you can see I have that zshrc file. I also have a bash_profile file that would be used if I was logging into the bash shell instead. That file won't be executed if I'm using the Z shell, in the same way that it would not load the Z shell configuration if I was using the bash shell. Let's try doing a configuration. Pick the file that's right for you, either bash profile or zshrc or whatever's right for your shell. And let's open that up with nano. So I'm going to do nano.zshrc. And you can see I've already got a little bit of code in there. We're going to come back and talk about what that means in just a moment. For now, let's just go above that, and I'm going to add some new lines. Let's do echo and then empty quotes. That's just a blank line. Let's do echo with the -in option, which suppresses the new line. And let's do welcome, comma, space, and then double quotes again. Now I'm going to do a semicolon and then type the command who am I. We know what the who am I command does. The semicolon just lets us put two commands on the same line. We could easily have a line return, but I'm going to put it right after it using that semicolon. Now let's do another blank line, and let's do echo -in. Today is space. And again, I'll use that semicolon, and we'll use the date command that we learned about, and then we'll do a new line again at the end of that. So now I've given Unix some commands, and it will run these anytime that I log in. I'll use Control X to exit out. And now we just have to load those commands. We can do those one of two ways. We could type source and then the file, and that'll tell it to read those commands right now. Or even easier in this case is I can just close that window and open a new one. And you can see what it does. Instead of just having the last login at the top, it now has our new code as well. So it executed that code when we logged in. This is just a simple demonstration. Throughout this chapter, we're going to be adding more configurations to these files. In this movie, we're going to learn how to define command aliases in Unix. The command that we use to work with aliases is alias. If we type alias by itself, it'll give us a list of the currently defined aliases. I happen to have a couple that got defined by Mac OS. You may not have any. That's okay. It doesn't really matter. It's giving us a list of the current aliases. What it's telling us is that if we were to type run-help, it would be the same as the man command. We can define our own aliases by also using the alias command and then giving it that same kind of equation. For example, very common and useful alias is LL. LL equals, and then in single quotes, let's put the command that we want to alias it to. ls space -lah, and then close my quote again. Now, whenever I type the LL command, it will be the same as if I had typed ls space -lah. I'll hit return, and let's try it out. LL. You see it worked. I get the exact same thing. LL wasn't a command that existed before, but I made an alias for it. Now, if I type the alias command, you'll see that it's listed there at the top of the list. You can see that my version has quotation marks where this one doesn't. I recommend always using them, especially if you're going to have a space that's in there, you're going to need them. Now, when we define an alias like this, Problem is it doesn't stick around. It's only an alias right now in the current shell. So for example, if I close this window and I open a new one and I type ll, you'll see it says command not found. And when I type alias, the list just has the original 2 again. But in the last movie, we saw how we can use configuration files to run commands at login. So if we put that alias command inside one of those files, it'll be executed every time we log in. I'm going to type ls-la because I don't have the ll command working right now. And here's the file that I'm going to be using for configuration. You might have bash profile or something else. Whatever file you're going to use for your configurations, we're going to edit that. So nano.zshrc for me. You can see we already have a couple of things in there from the last movie. I'm going to come right here and let's add an alias. So alias ll equals, we'll type the exact same thing we just had. Let's add another one for alias h is going to be equal to history. And then I'm going to hit a line return, and then I'm going to paste in a couple of them here so you don't have to watch me type them. You can pause the movie if you want to type them. Here what I'm doing is I'm redefining existing commands in order to add options. So I'm aliasing the mv command to instead be mv with the -i option for interactive. And I'm doing the same thing for copy and remove. For make directory, I'm always using the -p option. And for df and du, disk free and disk usage, I'm always using the -h option to show sizes in human readable format. So you can have aliases that just create shortcuts to common tasks, or you can redefine a command to add options. Another way you could use aliases, they can be used to fix common typos. Let's say that you frequently find yourself mistyping a word. Let's say pwd. You could have pdw equals pwd. Now, whenever you typo it as pdw, it'll actually run the real command, the path to the working directory. Once we've got all our aliases in there, let's use Control X to exit out, and we'll save those changes. If I want those changes to take effect, I have to either log back in by closing the window, or I have to tell it to reload that file using source. Source and then dot, and then whatever the name of the file is that you're using. Maybe that's bash profile. In my case, it's zshrc. You can see that it goes ahead and acts like I just logged in because it runs the code that's in there. And in the process, now I have my aliases. Let's try H. Let's try DF. You can see that it worked and it gives me human size for that as well. Or instead of PWD, if I do PDW, you'll see it still returns the correct path to my working directory. There's no set way that you have to use aliases. They're a tool for you to use in a way that makes your work more efficient. If you find yourself performing an action over and over again, it may be worth adding an alias. In this movie, we're going to learn about environment variables and how to set the path variable. Environment variables are dynamic named values in Unix, and they're used by commands and applications. The fact that we can set them to different values means that they function a bit like settings for the Unix environment, and they can affect the way that commands and applications do their work. If we want to have them work differently, we can set different environment variables. Setting environment variable is very easy. We just set the name of the variable in all capital letters equal to something in quotes. It's a best practice to put export in front of it to ensure that the variable is available in the current running program as well as any subprograms that might get launched. So for example, I could create a new environment variable called full_name, set it equal to my name, and export that. Now setting this environment variable won't have any effect unless part of the Unix environment or one of the programs that you're running is looking to this value and making use of it. We're going to be looking at two variables that are built into the Unix environment and learn how to work with those. The first is going to be the path, and in the next movie we'll look at the prompt. In a previous movie, we learned how we can view the path. We can use echo and then space with a $sign and then the name of the variable in all capitals, echo path. And this returns the current path that my system is using in order to find commands. Yours may be different than mine. It doesn't really matter. It's just telling Unix these are the directories to check in whenever you type a command name. Go look in these places and see if you can find it. And not only look there, but look at them in that order. We could set the path from the command line, but just like we saw with aliases, those environment variables won't stick around when we close our window. If we want them to stick around, we need to put them in one of our configuration files so that they're always set up when we first log in. So I'll type ls space -la, and my configuration file is going to be that zchrc file. If you're using bash, it might be the bash profile or something different. Let's open up that file using nano.zshrc for me. And in here, after we have our aliases, I'm just going to skip down here. You can see I actually have one here. We'll talk about that one in a moment. I'm going to create a new one here for the path. There's no $sign in front of it this time. And that path is going to be equal to some string. Now I could put in the exact same string that I had before. Let me just open another window here so we can see that. We can have the two side by side then. Here we go. And let's just do echo $path. Now I could just copy this and bring it in here and paste it in, and then I could make changes to it. Maybe I want to add a directory. Let's say, for example, that I install another program like MySQL, and so I want it to look for programs in the MySQL directory. Well, then I could add colon and then whatever path goes to that. user/local/mysql/bin. That's a common location. So now, when I log back in, this variable will be defined, redefined in fact, and it means that whenever I type a command, it'll first look for it in this directory, then in this one, then in this one, then in this one, and if it doesn't find it in any of those, the last place it'll check is in that MySQL directory. So I've now told it to look somewhere new for new commands. This would work, but there's an even better approach. We know that the value of the current path is stored in this variable right here with the $sign. So instead of retyping all of this, instead let's move our cursor over here and let's just delete everything that's there. And in its place, let's type $path. Now what this tells it is take the existing path that you have, wherever you got that from, whatever path is when you come into this file, use that, but then also add this to the end of it. That way, if for some reason this path were to change, it wouldn't potentially break things here. All I'm doing is adding an element onto the end of it. We can now exit out of here, Control X, let's save our changes. And now we need to either reload this file or we need to close the window and reopen it. I'll use source.zshrc to reload the file. And now when I say echo $path, you'll see that it includes that new location at the end. Over here in this window, it doesn't include it still because it hasn't logged back in yet, right? It's only every time I log in now that that file gets executed. We can close this window and open a new one, echo $path, and now we can see that every time we log back in, it's going to set that value for us. Telling Unix how to look in new places to find new commands and programs is going to be something you'll do from time to time. By setting the path environment variable, it's easy to do. In the previous movie, we learned how to set environment variables, and now we're going to use what we learned there to set an environment variable for the command prompt. The command prompt is the bit of text that appears right here before every line that prompts us to provide new input to Unix. It can be fun and rewarding to set it to something that feels more customized and personal. We can do that using the environment variable ps1. If we use echo $ps1, we'll see the current value. For me, that's ks space and a $sign with a space after it. Yours will certainly be different. We can set it to a new value by setting ps1 equals, and then in quotes, whatever we want that string to be. So for example, let's try dash dash and a greater than sign and then a space at the end. It's always a good idea to have a space at the end because when it prompts us, you'll see that now there's a nice space between the prompt and where we start typing. Every time I hit return, you'll see I get the new prompt instead of the old one. Let's try another example. Let's try ps1 equals, and let's try what now space. Now every time I issue a command, you'll see that it prompts me with what now. A lot of Unix developers end up just using something simple like their username or the date or the directory that they're in. I might use my username like this, and that will output my username every time, or we can drop in a format code that'll do the same thing. Now this varies a little bit by what shell you're using. If you're on the bash shell, you'll use \u, but I'm on the Z shell, so it'll be %n. Now it displays my username, but it's actually using that %n to set it to whatever my username might be. If my username changed to something else, then the prompt would change as well. This table shows some common options that you might want to use and the format codes for bash and Z shell. So with bash, you're mostly going to be using backslashes followed by some character, and on Z shell, it'll be a %sign. So you can go down each of those and see you can have it put out your username, the current shell, your current working directory, the base name of the current working directory, that is to show the immediate directory that we're in. You can have it display the host name or the host name just up to the first period, the history number of this command. You can also put in dates. So you could, for example, have the date in various formats, 24-hour time, 12-hour time, or with the last one, you can customize it using a common time format called strftime. I'm going to use one where I use 1D to show me just the immediate directory that I'm in. If you were on bash, that'd be the capital W, \W. But I'll be using %1D. So you see that I'm in the Kevin Skoglund directory, so it doesn't look like I changed. But if I do cd into the my project directory, you'll see now it tells me that I'm in the my project directory. cd back to my user directory, and you'll see it tells me that's where I am again. Now, of course, this setting, like all environment variables, won't persist unless we put it in one of those configuration files. So let's add that as well, ls-la. This is the configuration file I'm using. You might be using bash profile or something different. I'll use nano.zshrc to open that up. And let's just jump down here in the file till we get to export path. And you can see that throughout this tutorial, the reason that my prompt has had that KS in front of it is because I had changed PS1 to be something different. So I'm going to change it so that instead of just being KS, that now it's going to be %1D, and you can add anything you want here. I mean, I could have KS colon in front of it, anything that you want, any text that you want, and that's what it'll display. So let's now exit out and save that. In order to get those changes to take effect, we either have to close our window and reopen it, or I can use source with the name of the file to have it read it in. And there we go. Now you can see that's my prompt. Who am I? And it prompts me again, KS followed by whatever directory I'm in. If I go into the My Project directory, you'll see that it puts that after it. How you decide to customize and use the command prompt is going to be up to you, and you can experiment with it over time to find something that fits your style.